surrounded by dark matter and dark energy, mysterious forces that permeate the universe and play a fundamental role in determining its evolution. Scientists can observe the effects of these cosmic enigmas, but as yet, they have found nothing.
Der Weltraum.
Space, an infinite vastness. But there's nothing in it. In a volume of about 13,000 by 13,000 by 13,000 kilometers, which is roughly the volume of the Earth, there's the mass equivalent of a small grain of sand. Not only that, when you examine this grain of sand, you find it consists of ghostly particles. Particles that pass through everything without leaving a trace. And then there's dark energy. What exactly are dark matter and dark energy?
Around 13.8 billion years ago, our universe began with an explosion, the Big Bang. It was the birth of matter, space, and time, the beginning of everything. Astronomers estimate that the visible universe contains approximately 2 trillion galaxies, each comprising 100 billion stars. But despite this, the universe is eerily empty. Modern cosmology traces the universe back to its beginnings. They are in search of the blueprint for everything, and in doing so, look deep into the past.
What we see today is the end result of a lengthy development process. When we look out into space, we're always looking into the past, and the deeper we look, the further into the past we look too. We don't believe that different areas of the universe develop differently, but that generally speaking, the universe always appears roughly the same everywhere.
Astronomy is a voyage of discovery into the infinite, always at the limits of our imagination. After the Big Bang, stars, nebulae, galaxies, and ultimately planets and even life came into being. Researchers are increasingly able to recognize and understand the complex structures and interrelationships in the cosmos, and are learning ever more about the objects within it.
We have galaxies, galaxy clusters, and galaxy superclusters. These are absolutely enormous structures. And we have the stars in the galaxies. There's matter between the stars. And we have certain types of stars that are all different. The galaxies are different too, and we have exotic objects like black holes. So there's a whole zoo of different star types, galaxy types, and types of matter in between.
Our knowledge about the universe has increased exponentially in recent years. But what we can actually see or detect only makes up a fraction of everything there is. There must be much more out there that influences the universe and governs its evolution. A mystery that we cannot comprehend. Large amounts of matter and energy that have yet to be proven by any scientist. Dark matter and dark energy.
What's really intriguing is that experiments indicate that we've only actually seen roughly 5% of our universe. The universe consists of 5% matter that we see all around us, roughly 25% so-called dark matter. That is, matter we can't see. And then a further roughly 70% of stuff that physicists don't have a clue about what it could even be. So they gave it a spectacular name, dark energy.
Dark energy and dark matter. Concepts that ultimately reflect the current state of scientific knowledge. Astronomers notice the effects these mysterious forces have, but are otherwise in the dark.
Da stimmt irgendetwas nicht.
Something doesn't add up.
Das führt man auf
And that leads us back to a gravitational effect.
zurück.
And we say it's due to dark matter.
Dunkle Materie.
When we consider that there was a Big Bang,
Urknall gab.
And since the Big Bang, the universe has been flying apart. Then you quickly come to the realization without further calculation that this expansion ought to slow down due to gravitational attraction. But it isn't. It's accelerating. So we introduce the concept of dark energy that causes the universe to expand. They're both just concepts that say, we have no idea.
Dark matter and dark energy seem to be ubiquitous and permeate everything. They are among the biggest mysteries in our universe.
A grain of sand within a region of space the size of the entire Earth. If you were to examine 6 of these grains of sand, you'd discover that 5 of them have very strange properties. They're basically invisible, which is why we call them dark matter. This dark matter, nonetheless, has a considerable influence on our universe, as it slows its expansion. And because we can measure this slowing very well, we can accurately determine the amount of dark matter there must be. Could it be that this dark matter is composed of black holes? That's a good question. It could be that there are many, many, many black holes finely dispersed throughout the universe. In order to answer this question, however, we first have to understand these black holes better. And it would help us to do so if we could obtain an image of a black hole. And this is exactly what scientists succeeded in doing in 2019.
It's an historic picture that astronomers presented in April 2019. For the first time ever, a global network of radio telescopes photographed the silhouette of a black hole. Black holes are the most compact form of matter we know of. Gravitational monsters that devour everything around them. Not even light can escape from them.
It was an amazing moment. It's an extremely difficult job. You can't see a black hole because it swallows all the light. But if you have a black hole here, and you're here, and on the other side there's a bright star, the rays of light from this bright star get bent around the black hole. And because it's here, a bit arrives everywhere. All of a sudden, you see a ring of light surrounding the black hole. And we actually found this. It's moments like these that, if you have a bit of feeling for such things, really make your heart sing and you say, black holes, they're not made up, they really exist.
No single telescope, neither in space nor on Earth, would be powerful enough to capture such an image. So, the scientists used a trick.
For an image like this, you need a telescope the size of the Earth. If you want a telescope that's as big as the Earth, you make it from separate telescopes that together act like a single telescope. All of the individual images are then processed to create a single sharp image using interferometry.
The Global Telescope Network created an enormous virtual instrument, the Event Horizon Telescope. It doesn't work in the visible spectrum, but captures radio waves. It's colored red so that it can be seen by the human eye. The black hole being observed is 6.5 billion solar masses and is at the center of the Messier 87 galaxy in the Virgo constellation, 55 million light-years from Earth.
We find black holes so fascinating because inside black holes, physics more or less stops working. Time basically comes to a standstill inside black holes. If you were passing by a black hole, you couldn't see into it, and we don't know what goes on inside them. That's what makes black holes so interesting. I think black holes became popular thanks to sci-fi films that depict how when something falls into them, it gets ripped apart and everything gets destroyed. It's actually correct in a certain sense because gravity is so strong inside black holes that ultimately everything gets obliterated.
There are countless black holes in our galaxy too. The largest by far is at the center of the Milky Way, 26,000 light-years from Earth. Sagittarius A star, a supermassive black hole of around 4 million solar masses.
The main thing a black hole does is attract other stars and bodies. It's an enormous mass that exerts a large attractive force on everything. So the assumption was that if you look carefully, you should see objects orbiting the black hole at high speed. The same way you can determine the mass of the sun from the motion of the Earth, you can determine the mass of the black hole from the motion of the stars orbiting it. That's why we started measuring the trajectories of the stars close to the black hole very precisely.
Sagittarius A star is actually rather unremarkable, but now and then we observe sudden spikes in brightness. This happens whenever matter falls into the black hole. The Chandra X-ray telescope detects these outbursts too. Chandra first observed Sagittarius A star in action and saw the black hole devour matter at the beginning of the 2000s. Sagittarius A star is a valuable source for astronomers studying the conditions in the vicinity of a black hole. In May 2019, scientists detect an extremely bright flare-up. Sagittarius A star suddenly lights up twice as intensely as usual. The black hole in the center of our galaxy had apparently grown hungry. The flare-up happens on the event horizon of the black hole, the boundary beyond which matter and energy irrevocably fall into the gravitational abyss. Beyond this threshold, nothing can ever escape.
We, of course, asked ourselves, what was that? What did we just observe? Something must have fallen in, or the black hole wouldn't have emitted light. They gain gravitational energy, and this is released as radiation, and that's the flash we see. But what was it exactly? Maybe it was a rogue planet that was traveling alone and fell in, or a small gas cloud. As the light emission wasn't that big, it must have been a compact body that fell in quickly.
The observed event actually took place in the distant past, 26,000 years ago. That's how long it takes the light from the center of our galaxy to reach us. But there are other black holes quite near to our planet. In the spring of 2020, scientists at the European Southern Observatory detected one, approximately 1,000 light-years from Earth. 1,000 light-years. On a cosmic scale, this black hole is right next door to us. It's a so-called stellar black hole in the star system HR 6819, and only about 5 solar masses in weight. Together with 2 stars, it forms a triple star system. Small black holes like this are created when a star nearing the end of its life explodes as a supernova. The outer shell of the star is ejected, and the core collapses in on itself to form a black hole.
1,000 light years isn't very much, but this black hole is very docile. That is, it doesn't attract matter because there's none around. There's no gas in the vicinity. The stars are far enough away that they don't get ripped apart. And as long as it stays that way, the situation there will remain stable, and we'll have nothing to fear.
April 2018. A SpaceX Falcon 9 rocket lifts off, heading for Earth orbit. On board, NASA's TESS space telescope. TESS's actual job is to find exoplanets. To do this, it systematically scans the night sky. The telescope also observes a galaxy in which an unusual brightness distribution was detected. With the help of TESS, the researchers were able to observe almost from start to finish a star being torn apart and devoured by a black hole. Such a stellar death is very rare. The observed event played out around the supermassive black hole in the center of a galaxy in the Volans constellation, about 375 million light-years from Earth. Once the star enters the gravitational pull of the supermassive black hole, its fate is sealed. It was approximately the size of our Sun. The gravitational attraction of the massive object deflects the star from its trajectory and subjects it to enormous tidal forces as it nears the event horizon. These eventually tear it apart.
It heats up unbelievably. The star is turned into a disk that lights up extremely brightly, and when it lights up, it loses energy and moves ever nearer to the black hole until all of a sudden it's gone.
Black holes, gravitational monsters that devour everything in their vicinity. Not even light can escape from them. For a long time, they were purely theoretical. But nowadays, we can observe them and are learning ever more about these invisible concentrations of gravity. Black holes are simultaneously one of the dark secrets and most fascinating objects in our universe. Anything that gets too close to them is inevitably doomed and no longer of this world. Not even light can escape from them. Proving that they really exist was a landmark in astrophysics. Scientists speculate that there's a totally different mystery in the outer regions of our solar system, an enigmatic ninth planet.
We've had super telescopes out there in space for decades now. The Hubble telescope, the Kepler telescope, that allow us to see even small planets in distant solar systems. And now these astronomers come along and claim there's a ninth planet in our solar system. Why do they think that? Well, they say there are objects out there beyond Pluto that move very strangely, but they can't see anything. And that's why some astronomers say, well, if we can't see anything, this ninth planet could be a small black hole.
We can see Mercury, Venus, and Mars with the naked eye from Earth, Jupiter and Saturn as well. And they move as we would expect them to. Uranus was discovered by William Herschel using a telescope, but its orbit was different than expected. This could be an indication of an as yet undiscovered mass in our solar system.
There are clever mathematicians that then take these discrepancies and make a prediction about where another planet would have to be. A troublemaker disturbing the orbit. They then looked closely and discovered Neptune. It was a tremendous success for observational astronomy, of course. So people said, since that worked so well, maybe we can continue doing the same thing. So they carefully scrutinized the orbit again and concluded it still wasn't right. Something else must be out there. And then they found Pluto. And now people are saying it still isn't right. Something else must be out there. Problem, though, is that the further out we go, the more slowly the planets move. And it takes more and more time before we can see the disturbances. This means that the uncertainties regarding where the next planets are get bigger and bigger the further away they are. So we haven't managed to track down another planet yet. We don't even know whether we're looking for one object or perhaps several. It's just speculation. But there are indications that the orbits aren't totally undisturbed. So some of my colleagues do believe there could be something there.
The object would have to be about 6 times the mass of Earth and be far outside the orbit of Neptune. Astronomers speculate that there's a cloud of debris here that encloses the solar system like a shell.
About where Pluto is located is where the Oort cloud begins, a large quantity of small clumps of matter that also move around the Sun. But we've only known about this cloud composed of many smaller objects since 1990. And it's because of these smaller objects that Pluto lost its planet status. It's possible, of course, that another, somewhat larger planet is hiding in this Oort cloud too.
Up until 2016, Pluto was known as the 9th planet in our solar system. But as more and more objects of a similar type were discovered, scientists reconsidered the planet definition. Pluto was demoted to the status of dwarf planet and has since then shared this status with 3 other objects. They are all so-called trans-Neptunian objects, a collection of innumerable pieces of debris beyond the orbit of Neptune. Many of these trans-Neptunian objects have orbits that are similarly aligned. This is unusual, and so we concluded there was a common unknown cause: Planet 9. It was an anomaly in the orbit of Uranus that led us to discover Neptune. But this method doesn't seem to be working this time around.
The disturbance of Uranus was so large that it was possible to predict relatively accurately how big and where the planet had to be, and it was discovered accordingly. Someone predicted it had to be there. A telescope was pointed in that direction, and sure enough, there it was. We can't do that this time, as the disturbances are so small that they might not even be real. So in this respect, we're still a bit in the dark, literally.
There's another theory that tries to explain the unusually similar alignment of some trans-Neptunian orbits. There could be a primordial black hole in our solar system. Stephen Hawking described such primordial black holes in the 1970s. In contrast to all other black holes, it is thought that countless numbers of these very small objects were formed shortly after the Big Bang.
It's a theory. We haven't found any yet. You can search for them by observing the light from distant stars and galaxies, for instance. If small black holes were to pass by, they would bend space-time. You'd see abrupt fluctuations in luminosity, peaks. But this hasn't been observed yet, so at the moment there's no evidence that they really exist. It's just one possibility of the hypothesis, nothing more.
A black hole orbiting in our solar system could explain the strange trajectories of some trans-Neptunian objects. After all, it's just a question of mass and its effect.
It's actually irrelevant whether you say planet or black hole. It's an object that exerts a gravitational force. A black hole exerts a gravitational force, and a planet would exert a gravitational force. It would be impossible to distinguish between the two. Maybe a black hole sounds better than planet. If you say black hole, you're sure to get people's attention. The fact is, you can't make any distinction between the two.
The hypothetical object is estimated to have approximately 6 Earth masses. A black hole like that would be tiny. It would have the diameter of a grapefruit.
Could Planet 9 really be a black hole? Let's first take a step back and ask ourselves what evidence there is for a 9th planet. Well, say the astronomers out there beyond Pluto, there are 6 small objects whose elliptical orbits are similarly aligned. But the alignments of elliptical orbits are always random, so it could also be 6 coincidences. And I find it unwarranted to use such an extravagant explanation as black holes for an argument as weak as this. But astronomers continue to look for Planet 9 nonetheless. But if you ask me, they won't find much.
In our universe, we see the entirety of space and time, matter and energy. And in between, nothingness, seemingly empty. But we know from observations of stars in galaxies and galaxies in galaxy clusters that there must be far more mass present, which is affecting the motion of objects in space. You just can't see it. Scientists are searching for this missing mass, which they call dark matter, due to it being invisible. But physicists are uncertain as to what it could be composed of. The scientists can only detect the effects this missing mass has. Dark matter interacts through gravity. Stars and galaxies simply do not move in accordance with the gravitational forces of the matter that is visible to us, and thus demonstrable.
In order to understand this strange behavior of the universe, there has to be more mass out there that we cannot see. Therefore, dark matter. But this dark matter has some very strange properties that I would like to explain to you now using this. Let's pretend this pen is made of dark matter. What would this mean? It means that light couldn't interact with this matter. It couldn't be reflected, for example, so you wouldn't be able to see it. It isn't just light that can't interact with dark matter, though. Even normal matter like my hand is unable to interact with it. What does that mean? If I tried to grab this pen, it would pass through my hand. I couldn't grasp it at all. That's what dark matter means. And not only that, if this pen were made from tiny particles of dark matter, they would be spread throughout the cosmos. There would be vast numbers of tiny particles, billions each second, constantly passing through our bodies, and we wouldn't notice a thing. That's what dark matter means.
Our Earth orbits the Sun, apparently unaffected by dark matter. Dark matter is evenly distributed over the relatively short distances in our solar system. So the disturbances it causes come from all directions simultaneously. As such, it has no overall effect. It neither radiates nor reflects light. We can neither see it, nor does it affect us. But it must be there nonetheless. Scientists assume that dark matter, like visible matter, is a product of the Big Bang and only affects large structures, like galaxies.
The sun's motion is much too fast, so there has to be matter somewhere else. And further out in the galaxy, the situation gets worse still. There, the stars are moving even faster relative to the speed they ought to be moving at. And this additional speed can usually only be caused by a mass. But we don't see it. This is why it's called dark matter, because we don't even know where it is and how we ought to interpret this. It's a mystery. Something must exist in the neighborhood of the sun that makes up this dark matter, and we don't have a clue as to what it could be.
On the basis of measurements and calculations, scientists deduce what the mass of the dark matter in the universe must be and how it is distributed. Whether it consists of one type of particle or several different ones cannot be said with certainty.
In an astronomical sense, dark matter is like a bucket of coal. It's there, but you can't see it in the coal bunker when it's dark. And we're in a similar situation. There's some matter out there that we can't see and are trying to find. But it's eluding our best efforts. It's very peculiar and is commonly referred to as dark matter.
So, dark matter is basically massive elementary particles, or perhaps numerous primordial black holes that we cannot detect. But they're responsible for the motion of stars and galaxies not obeying the laws of physics.
There appears to be 5 times as much dark matter as visible matter, so we have to be colliding with it all the time. But that's not a problem, since dark matter interacts via gravity. It doesn't interact with us in any other way. Dark matter isn't charged, we can't feel it, and it doesn't exert any other force on us. As such, the forces that dark matter exerts on us are themselves weak.
The purpose of the German X-ray telescope eRosita is to gather information about the structure of the cosmos and its evolution. It's generating a map of the X-ray sources in the universe. And it's hoped eRosita will provide new insights into dark matter and dark energy. To this end, the telescope scans the entire sky, primarily surveying so-called galaxy clusters. Gigantic aggregations of thousands of individual galaxies that are bound together by the force of gravity. It's about understanding cosmic evolution and the interdependencies in our universe. Dark matter acts as an attractive force through gravity, whereas dark energy drives matter apart. Based on its observation of galaxy clusters, eRosita should help scientists better understand the interplay between these two mysterious forces. The data will be used to create a map of the skies, an image of the universe and its evolution.
Dark matter can simply pass through us without causing any injury. X-rays can penetrate us too, but they would harm us. There are forms of radiation that can pass through us and are not harmful, though. Neutrinos, for example, are particles that pass through us without causing injury. And dark matter could be composed of particles that don't interact with us at all. They are incapable of interacting with our particles, so they can pass through us without causing harm.
We know nothing about the particles that dark matter must be composed of. Although it constitutes over 80% of the matter in the universe, we've not yet succeeded in directly detecting even a single particle of dark matter. But entire galaxy clusters must be filled and surrounded by dark matter. The galaxies within them rotate much too fast. Without the additional gravity, some of them would have long been scattered in all directions. Dark matter permeates the entire cosmos, but it only makes its presence felt through its gravitational interaction with normal matter.
Whether it consists of small elementary particles or large elementary particles or clumps of something, we don't know. There are even those who say it's black holes. That would be worse if there were that many black holes here with that much mass to cause the Earth to move so fast around the center of the Milky Way.
Dark matter leaves behind traces in the universe. That it's actually composed of massive particles is a basic assumption. If this assumption turns out to be incorrect, classical physics would have failed.
They're investigating something without even knowing what to look for. I mean, if you want to know how bright a light bulb is, you have a specific job. But if you say, I'm looking for something, but I don't know if it even exists, I just see the effect of something, you're in a rather difficult situation.
Da ist man schon ziemlich in einer schwierigen Situation.
An even greater puzzle in modern physics than dark matter is dark energy. It appears to steer the fate of our universe as a whole.
There's something out there, namely dark energy, that accounts for 70% of all the mass and energy in our universe. What on earth is it? What we do know about it is that it's finely dispersed throughout the universe. Not just in empty space, but everywhere, in every body, in my body, in your body. What we also know is that it's also called ground state energy. What does this mean? It's the energy of the overall state of the universe. And because there's nothing lower, it means you can't tap into the energy to power something. For instance, like a smartphone or a car. We also know that this dark energy has the effect of causing space to expand, like yeast causes dough to expand. Isn't that odd? And there are now several space missions to find out exactly what it is.
Dazu gibt es jetzt mehrere Weltraummissionen.
Like the Hubble Space Telescope before it, NASA's Nancy Grace Roman Telescope will provide us with brand new insights into the wonders of the universe. The telescope is named after cosmologist Nancy Roman. In the mid-1950s, she established the Space Astronomy Department at NASA. The main objective of the telescope that bears her name is to investigate the distribution of galaxies in the universe and collect important data about the mysterious dark energy that permeates the cosmos and apparently causes the universe to expand ever faster.
What we observe in the universe is essentially radiation that interacts with matter. That is, solid material, tables, chairs, coal, rock, gas, etc. And at some stage, it has to emit light, and we can see it. But we've discovered that there are other forms of energy and matter in the universe that we can't see. The universe expanded. Then this expansion slowed down, but now it's speeding up again. Why is that? It's thought to be caused by some form of energy that we can't see, dark energy. And it too contributes to the total composition of the universe. All things considered, matter only makes up a few % of the entire universe, most of which we cannot see.
The Sloan Digital Sky Survey, or SDSS project, was set up to survey the night skies. For over 2 decades, the detectors have been measuring the position and brightness of around 470 million celestial objects. The result is a 3-dimensional map of the universe, which also provides insights into the effects of dark energy. The results support the theory that dark energy is the driving force of our universe.
Dark energy is, in a sense, something used to explain a physical process. Dark energy is a bit like anti-gravity. We know that gravity attracts masses. It's attractive. We see that the universe is expanding, and in actual fact, this expansion is accelerating. So there must be something that drives masses apart too. That's what this dark energy is. We don't have a clue what it might be, so it was initially given the name dark energy. But we really don't have any idea what it is.
Richtig wissen, was das ist, tut man überhaupt nicht.
Europe is also working on a dark energy hunter. The Space Telescope, named after the mathematician Euclid of Alexandria, is intended to help us understand why the expansion of the universe is speeding up. The telescope that the scientists and technicians are working on will observe the heavens in the visible and infrared spectrums simultaneously. Euclid's objective is nothing less than studying the evolution of the universe over the past 10 billion years. Within 6 years, the telescope will map out an impressive 1 billion galaxies. Dark matter and dark energy have a significant influence on our universe. Whatever they may be, the structure of the universe and its evolution are clearly dominated by these mysterious sources of force. Scientists are searching for the as yet unknown elementary particles of which dark matter must consist. But they still haven't found any traces of these hypothetical building blocks.
Dunkle Energie, was ist das eigentlich?
Dark energy. What is it actually? It's a property of empty space, of the vacuum. I'm going to draw a piece of the vacuum represented by this box. Now here's the thing. In the last century, a physicist named Heisenberg showed, and we know that it's true, that in such a vacuum, pairs of antiparticles pop briefly into existence. Here, for example, a negatively charged electron and positively charged positron that mutually annihilate shortly thereafter. And this is happening everywhere. Negative and positive. Everywhere in the vacuum. So why do we need something like this? Because it allows us to understand how an electromagnetic wave, which consists of a positive electric field and a negative electric field, is able to propagate. This wave has a polarizing effect. It drives the two virtual particles apart. And so we understand the propagation of light in a vacuum to be nothing more than the polarization of these virtual particles. With that, we finally understood it. But we now know that we need these virtual particles to explain how the universe, how space is being driven apart, because virtual particles scatter apart.
Could the vacuum energy really be the enigmatic dark energy, and thus have a significant bearing on Einstein's cosmological constant and the evolution of the universe? A natural assumption that many scientists go along with. But there still isn't a convincing model that would give this assumption a solid foundation.
Den einzigen Erklärungsversuch, den es
The only attempt there has been to explain dark energy so far is on the basis that it could be the vacuum energy. This sounds like a contradiction, since vacuum is actually nothingness. How should it contain energy? Our current understanding is that in the vacuum, new particles are continually being created and annihilated. This happens so quickly that we're unable to observe it. So what we see as a vacuum is an average condition, which is the result of so-called virtual particles being constantly created and annihilated. And they have an energy, so you can assign an energy to the vacuum. And this vacuum energy could be the mysterious dark energy. But when you do the sums, however, you come to the conclusion that although it's a nice explanation, the numbers don't add up at all.
A whole new generation of detectors is being constructed in order to shed light on dark matter. Among other things, scientists are looking for WIMPs, the favored elementary particles that could make up dark matter. Weakly interacting massive particles. But so far, we haven't been able to prove their existence.
The term WIMP stands for weakly interacting massive particles. That is, large elementary particles with mass, but that we can't see. But that's hypothetical. CERN is currently investigating. There are research projects trying to confirm the existence of WIMPs. You would have to be able to detect them on account of their momentum. So, conservation of momentum is a huge topic, but we can't find them. CERN has launched a research program, but at the moment we still don't know what it is.
Researchers are taking various and sometimes contradictory approaches in their search for the mysterious particles of which dark matter is thought to consist. But so far, they haven't been able to find anything.
Physicists always come up with interesting names, like WIMPs. There are also MACHOs, massive astrophysical compact halo objects. These are just objects, such as planets, that don't orbit a star and are dark. They emit so little electromagnetic radiation that we can't see them. Or so-called brown dwarfs, that are almost stars, but don't shine. There would have to be a great number of them that we don't see in our observations of the sky, but that contribute to dark matter.
Albert Einstein occupied himself with the question of how the universe behaves as a whole. When the great thinker formulated his field equations for general relativity, it was still believed that the universe was static. However, his equations were only able to describe this static state if an arbitrary constant was introduced, the cosmological constant. a number that made his theory correspond with the accepted reality. But when it was demonstrated that the universe was in fact expanding, Einstein rejected this constant again.
Einstein's cosmological constant. Which is it actually? In his equations, this cosmological constant had the effect of causing the universe to expand. And this is exactly what he needed at the time, because people believed that the universe would have to collapse due to the mass it contains. But they observed a static universe, so the cosmological constant was needed. A few years later, however, a certain Mr. Lemaitre and Mr. Hubble came along and said, "We can see that the universe is expanding." So Einstein says, "I'm an idiot. I didn't need this thing after all." The situation is very different today. Sure, we see that the universe is expanding, and so don't need a cosmological constant for that reason. But then in 2010, a certain Perlmutter comes along and says, "I can see that this expansion is accelerating. So I need a cosmological constant again." So today, Einstein has been proven right again. On the other hand, there are astronomers who doubt whether the expansion really is getting faster. They claim it's simply an observational error. And then there are some physicists that say dark matter isn't made up of mysterious particles. It must be something else. Does this mean cosmology today is in a crisis?
The general consensus is that this enigmatic dark energy, which accelerates the expansion of the universe, can be simply described by Einstein's cosmological constant. But there are doubts, too. Some scientists even want to revise Einstein's entire theory. Some researchers simply doubt the correctness of the measurements of the increasing expansion of the universe.
Measuring distance in space is a fundamental discipline in astronomy. If there's one thing that has been repeatedly verified over the centuries, it's distances. You can be wrong, of course. There's always a margin of error of 1% or 2%. But if we are fundamentally wrong about the distance to the galaxies, then we have a fundamental problem with the whole of cosmology too. And if something is fundamentally wrong there, I'd say we have a problem with space-time, because it's giving us false information. I don't think so personally. Einstein had been right up to now, and I believe that will remain the case in the future as well.
Einstein's theory is a theory of gravity of masses in the universe. We can see dark matter due to its gravitational effect on the motion of stars and galaxies, but it still remains a mystery to us. And not all scientists are convinced that the expansion of the universe is speeding up. The proposed cause would be a mysterious force, dark energy. Here, too, we currently only have hypotheses to draw on.
I personally believe that these distance measurements are all correct. That means that accelerated expansion is real. The cause is dark energy, and that in turn is virtual particles in empty space. The real problem is dark matter, because we've been looking for these elusive fundamental particles for decades and have still found nothing. And then there are the primordial black holes, a kind of baby black hole left over from the beginnings of our universe. But to be honest, that sounds rather obscure to me. So, will we at some point be able to resolve the problem of dark matter? I personally firmly believe we'll get there at some point in time. And until then, things will remain really exciting.
Dark matter and dark energy. Together, they make up 95% of the universe, according to the scientists' theories. But they have yet to solve the puzzle. And so, the vast majority of our universe remains a mystery, hidden in the darkness of space. Gravity. force that nothing and nobody can escape. This mysterious force envelops and permeates us, and not only dictates our life on Earth, but holds the universe together. Gravity is the key to understanding the universe.
Gravitation.
Gravity. Everyone seems to have an intuitive grasp of what it is. You have two objects, they attract one another, and that's gravity. But when you delve deeper, it's actually a rather complicated matter. Take weightlessness in space on the space station. A marvelous state. You float in your sleeping bag, food flies into your mouth. When you close your eyes, you instantly get the feeling there's no up or down anymore, because there's no force acting on your equilibrium organ. Does this mean that the Earth's gravity isn't there anymore? Of course it is. But there must be some sort of opposing force canceling it out. But I'll tell you more about that later. Interestingly, weightlessness can be experienced on Earth too, namely on parabolic flights.
A parabolic flight on a converted passenger jet. The airplane flies a so-called ballistic trajectory, a parabola. From level flight, the aircraft is put into a steep climb. During the ascent, the engines are throttled back. During the subsequent gliding phase, the passengers experience 0G for around 20 seconds. Weightlessness.
You first have to understand what weightlessness is. A common misconception is that weightlessness is synonymous with the absence of gravity. This is not the case. You're weightless when you're in a state of free fall. Every time I jump down from something, I'm in free fall. For a brief moment, I'm weightless.
That's the principle behind parabolic flight. The airplane and passengers on board are both in free fall, like a thrown rock. The pilots initiate the parabolic trajectory at an altitude of approximately 6,000 meters. Then they throttle back the engines. The plane continues to climb without accelerating, and from this moment up until they pull out, the jet is in a weightless condition for around 20 seconds. The flights are made in order to perform scientific experiments and also to prepare astronauts for their missions. And every now and then, guests are invited along to the 0G adventure too. Such missions are flown by experienced test pilots. During the climb and until the engines are throttled back, the passengers experience twice the acceleration due to gravity, 2G. Once thrust is removed, the weightless phase begins, 0G. The plane climbs until the Earth's gravity gains the upper hand and causes it to fall toward the ground. The pilots then initiate the pull-out maneuver. After a free fall of about 2,500 meters, they then level out again. During this maneuver, they once again experience twice the Earth's gravity, 2G. The plane flies several such maneuvers in succession during a mission. During the parabolic phase, there are 20 seconds of microgravity available for performing experiments. Any longer than that, and the airplane would get dangerously close to the ground.
The weightlessness we can experience on Earth usually comes to a fairly abrupt halt, due to the fact that we hit the Earth again, which is the negative part. But in principle, we can experience weightlessness in any form on Earth. If we want to experience it for longer, though, we have to go to the International Space Station.
May 2020, a Falcon 9 lifts off for the International Space Station. It's the first manned flight conducted by the private U.S. aerospace company SpaceX. The spacecraft is bringing the two U.S. astronauts Robert Behnken and Douglas Hurley to the ISS. The International Space Station has been in operation since 1998, a highly complex research laboratory in weightless conditions that's permanently orbiting the Earth. Or more accurately, that's falling around the Earth.
Schwerelosigkeit bedeutet, ich befinde mich im Freien.
Weightlessness means being in a state of free fall. I could naturally ask the question, why are they in a state of free fall in the space station? They're falling towards the Earth the entire time, but their horizontal speed is such that they continually fall past the Earth, which is why they're in free fall the entire time and thus weightless.
The International Space Station is the only place where scientists can conduct research on a long-term basis outside the influence of gravity.
Quarter-turn buckle test. 604 passes the pull test.
Humans are adapted to the Earth's gravity. And so the space station is also used to investigate the effects of microgravity on the human body. Researchers want to explore the solar system and travel to faraway destinations. Mars, in particular, has captured the imagination of scientists. But on the journey to Mars and back, explorers will be subject to zero-gravity conditions for many months. A manned mission to our neighboring planet would take 2 or 3 years in total. An unusual NASA study reveals what the consequences of such long-term missions could be for humans. The astronauts Scott and Mark Kelly are identical twins. One of them spent a year in the Earth's orbit. The comparison shows that weightlessness over a prolonged period of time causes muscles and bones to atrophy and impairs the cardiovascular system. It also affects the immune system and the eyes. In addition, long-term stays in space result in changes and damage to the brain and the genetic material of the astronauts, including to radiation exposure. In this way, the space station orbiting the Earth shows us how important the Earth's gravity is for the human body.
So what does an apple have to do with gravity? As every child knows, this is where Newton comes into play. But let's start with the basics. Here's the Earth, here's the space station. It feels the pull of the Earth's gravity, but doesn't fall to the Earth. Why is that? Well, there must be some opposing force that cancels out this attraction. And this is the so-called force of inertia. Every object, including an apple, that is accelerated builds up inertia, and we call this the force of inertia. And when I make it orbit, this inertial force points outward, and we call this centrifugal force. So now we can understand the space station. It orbits the Earth and feels its gravity. And because it's circling around the Earth, the centrifugal force balances out the gravitational attraction. So what did Newton see as he was sitting under the tree? There was an apple up here. It fell, and he noticed that it got faster and said, aha, acceleration, opposing force. Inertial force balances out the force of gravity. He jotted it down, and that was his famous law of gravitation. But the question remains, what exactly is gravity? And it's a question Newton was very successful in answering.
A falling apple is said to have led Isaac Newton to his laws of gravitation. Newton suspected that there was an innate force of attraction between the apple and the Earth. He also suspected that this same force governs the motion of the large objects in space. The celestial bodies interact with one another through some mysterious action at a distance. The greater the object's mass, the greater its pull. The birth of a revolutionary idea. The mathematician and astronomer Johannes Kepler had already described the orbits of the planets around the Sun in the early 17th century. The force that kept these planets in their orbits was then described in 1686 by Newton's law of gravity. It also allowed the elliptical orbits described by Kepler to be derived.
You have to admit it's one of the most brilliant ideas ever, that the force that causes an apple to fall to Earth is the same force that keeps the moon in orbit. I mean, you'd have to be pretty drunk to come up with such an idea. That the moon is falling towards the Earth the whole time, but always falls past it. It's falling the whole time, but whenever it tries to fall, the Earth has moved on. So it falls around the Earth and becomes a satellite. That was Newton's idea. He even sketched a picture of it. You can find this exact drawing in Newton's original book.
But where exactly does the Earth's gravity come from? A significant part is due to the Earth's inner core. The deeper down into the Earth you go, the greater the temperature and pressure become. At the center of the Earth, the pressure is then so high that the core is solid, despite having a temperature of over 5,000 degrees Celsius. This is where the mass is most concentrated. The relatively compact inner core constitutes a third of the Earth's approximately 6 sextillion tons mass.
The Earth's core is composed of nickel and iron. They're very dense, much denser than the rock on the surface, which is why the Earth's core plays a dominant role in the Earth's gravity.
The main thing is that the Earth has sufficient mass to hold on to an atmosphere. It's our planet's gravity that keeps the thin atmosphere bound to the Earth, essential for the emergence, evolution, and survival of life as we know it. The gravitational pull of the Earth forces the scientists into space if they want to experiment under weightless conditions. But this is also possible on Earth, using a trick.
You can simulate weightlessness simply by letting objects fall. You just have to increase the free fall time. And how do you do that? By building a tall tower and dropping something from it. You can even fire the object upward and allow it to fall back down again. In this way, you can increase the period of weightlessness a bit more. And then you have a few seconds in which to conduct experiments under weightless conditions on Earth.
And that's exactly what they're doing in the drop tower in Bremen, conducting experiments under weightless conditions on Mother Earth.
Orbiting research labs are difficult to gain access to. It costs a huge amount of money and takes a long time. So the obvious solution was to develop a test facility where you could create weightless conditions, at least for a short time, on Earth.
The principle of the falling apple gives the scientists in the Center for Applied Aerospace Technology and Microgravitation, or ZARM for short, 4.7 seconds of weightlessness.
In the drop tower, we allow experiments in drop capsules to fall. The drop capsule is basically a complete laboratory like you'd have on the ground. During the free fall time, it's weightless. We put the capsule in the drop tower, pull it to the top, pump all the air out of the drop tube so that nothing slows its fall later, and then let this laboratory, the drop capsule, fall.
The drop distance in the tower is 110 meters, 4.7 seconds to conduct the experiments. An important field of research at the drop tower is the behavior of liquids under weightless conditions. At the bottom, the capsule plunges into a deceleration chamber filled with polystyrene balls. The drop tower in Bremen is unique in Europe. Experiments under weightless conditions are carried out here on a daily basis.
We can see the drop capsule, which in this case is almost too long to fit in the deceleration chamber. We have to split it into two sections to get it in here at all. It's now being prepared for the next experiment. During the freefall time, we're investigating the auto-ignition of two neighboring fuel droplets under weightless conditions.
Inside the capsule is a complete laboratory, including lasers, cameras, and complex measuring instruments. Finally, a tip is fitted to the bottom end of the metal cylinder. It reduces the impact impulse when the laboratory, which by then has accelerated to 168 kilometers per hour, plunges into the deceleration chamber. The prepared capsule is then pulled to the top of the drop tube by winch and anchored in place.
The capsule is hanging at the top and gets dropped. It moves very slowly at first, so it doesn't feel much air resistance, but as it gets faster, the air resistance would increase, which would slow it. We wouldn't have microgravity, no weightlessness, which is why we have to create a vacuum.
Evacuate means creating a vacuum in the drop tower. To do this, it's sealed, and 18 high-performance pumps begin to suck out the air. The process takes about 1.5 hours. Once completed, the drop tube is almost devoid of air and has just 1/10,000th the normal atmospheric pressure.
The advantage of a drop facility on Earth is the excellent quality of weightlessness, the best achievable, in fact, even better than we can get in space. We have the possibility to improve things we didn't do well today, tomorrow. In space, we'd have to wait 10 years until maybe we get another chance.
In the control room, they monitor the evacuation procedure. The entire facility and the experiments are controlled from here.
We're currently evacuating the tower, which means we're sucking all the air out. The structure is sturdily built, of course. The entire tower is made from a long steel tube that's externally reinforced with rings so that it can't implode. If I take a bag and suck, it crumples up, and so this doesn't happen with the tower. It's fitted with reinforcing rings and is engineered accordingly.
Researchers from around the world conduct up to 800 experiments a year in Bremen.
When we're ready, the experimenter decides when to launch. We specify the time window and say, "Ready when you are."
The scientists now take control of the experiment. The last of the cables are disconnected from the capsule.
Authorization, please.
The moment of launch. Quiet, unspectacular.
Release.
The retaining hook is disengaged. The laboratory drops. 4.7 seconds for the scientists before the laboratory lands in the deceleration chamber. The initial evaluation begins immediately afterwards. After the drop, the tube is filled with air again, and the laboratory retrieved from the deceleration chamber and freed of polystyrene balls. The big advantage of the drop tower: the morning experiment can be repeated again in the afternoon. The free fall time can be increased to 9.3 seconds. In this case, the laboratory capsule isn't dropped, but fired upward by a catapult in the foundations of the tower. The catapult launch doubles the distance the capsule travels, and thus the freefall time as well.
The moment the drop capsule leaves the catapult, that is, no propulsive forces are acting on the capsule, just gravity, the capsule coasts weightlessly upwards, slows down, changes direction, and falls back down along the same path. If you were in the capsule, you wouldn't notice it getting slower, stopping for an instant, changing direction, and falling down again. In this way, we can almost double the experiment time from 4.5 to 9.3 seconds.
Thanks to the frictionless free-fall flight, the scientists at the Center for Applied Space Technology and Microgravity can eliminate the effects of the Earth's gravity for a short time. The drop tower in Bremen allows weightlessness to be achieved on Earth, and does so several times a day. Gravity governs our lives, but anyone can escape its grasp for a short time.
You can experience true weightlessness even on Earth, but only for a brief time. Take a swing, for example. It swings up, reaches a turning point, and then swings back again. At the moment it becomes slower, the force of inertia is pointing upward and balances out the downward force of gravity. It's the same thing with a trampolinist, as we see here. From the moment he jumps up, he gets slower. The force of inertia is upward, the force of gravity downward, and he's really weightless, even if it's only for a few seconds.
As familiar as gravity seems to us in our everyday lives, it's nonetheless puzzling. Newton's law of gravitation was a milestone in physics. It not only explains motion under the influence of the Earth's gravity, but also how the stars, planets, and entire galaxies move in the universe. In 1915, Albert Einstein presented a totally new view of the universe. In his general theory of relativity, he treats gravitation not as a force, but as a property of the geometry of space and time.
In his view, gravitation was geometry, so objects don't attract one another because something somehow falls down. They're attracted because space-time has a particular geometry. That's very difficult for us to imagine because we can only think three-dimensionally. To do so, we have to think in higher dimensions, as it were. We humans can't do that. You can only do it on paper with mathematics. But it does mean that if we know how much matter there is in the universe, we can work out the geometry of the universe, of the space in space-time.
Einstein's general theory of relativity and his new way of looking at the universe led physicists to discover a string of new phenomena and models. And his genius forms the basis of our modern digital life today.
Einstein first invented special relativity, which describes the situation for bodies moving at constant velocity, that is, not experiencing acceleration. He wasn't entirely satisfied with that, so he considered what happens in other situations. And the general theory of relativity makes allowance for accelerating frames of reference too. And he discovered that you could describe gravitation using such a theory. The clocks on board GPS satellites, for example, have to be corrected for this relativistic effect. In other words, if Einstein hadn't invented it, the GPS system wouldn't work. We'd continually get lost.
But even in the 21st century, while physicists and astronomers know a lot about gravitation, science is still a long way from understanding everything. But still, Einstein's contribution was a huge step forward.
Today, we know what gravitation actually is. A force field that an object, a mass, generates around itself. And what's great is that Einstein explained what this force field is. According to him, it's the distortion or curvature of space around an object. Take my body. The warping of space right next to me is much greater than further away. And the same applies in all three spatial dimensions. Another object creates its own distortion, and both these distortions can see each other, and that's what the gravitational force is. Because it's difficult to picture, we use an analogy. Instead of three-dimensional space, we use a two-dimensional surface. The depth of this funnel indicates how strong the curvature is. So down here, space is more strongly curved than further out. And if we accept this analogy, it's immediately apparent why planets, for example, move in elliptical orbits around another massive object. Here we see a planet orbiting the Sun. The Sun is here. You can immediately see that this is an ellipse. So we understand that curved space generates elliptical orbits. To summarize, gravitation is nothing more than the experience of curved space.
Einstein's imaginative power changed our picture of the universe overnight. Modern astronomy has been heavily influenced by his theories since then. Many astrophysical processes can only be satisfactorily explained using Einsteinian gravitation. One example is the gravitational collapse of massive stars toward the end of their lives. They collapse in on themselves to form a compact object like a neutron star or a black hole.
When the center of a star collapses, that is, when the external forces become so great that the atoms and the nucleons are no longer able to push back, the outer layers get squeezed more and more tightly together. At some point, the electrons orbiting the atoms are forced into the nucleus, and you're left with a neutron star. Basically, a huge atomic nucleus that's only held together by gravity. And these neutron stars exist and possess incredible magnetic fields and emit signals we can detect. If the mass of the star and thus the gravitational force is greater still, at some point you end up with a black hole.
Einstein's theory also makes a surprising prediction. For instance, that light will be bent by gravity. Evidence of this is given by so-called gravitational lensing. As with a glass lens, light from a distant object is bent by an object located between it and the observer. But much about the force of gravity is still shrouded in mystery. We know that objects attract one another. How strongly they attract depends on their mass and how far apart they are. If one body is much heavier than the other, it attracts it more strongly too. This effect could be clearly observed when the small comet Shoemaker-Levy passed by and was captured by Jupiter. The tidal forces generated by Jupiter's mass ripped the comet apart. The debris eventually crashed into Jupiter in 1994. Large masses attract small masses. Planets capture smaller celestial objects. One reason why massive Jupiter has so many moons. Many of them did not form in its vicinity, but when they approached the giant planet too closely, they were forced into orbit by its gravity. The second giant in our planetary system, Saturn, further demonstrates the effect of gravity. Its rings are formed by innumerable objects that are gravitationally bound to it. On a large scale, gravity is the dominant force in the universe, and it will eventually be responsible for its demise.
Our everyday experience teaches us that friction is all-pervasive, including out in space. But friction means a loss of kinetic energy, and when things slow down, their inertial force and thus centrifugal force is lower. And so the forces that oppose gravity are constantly diminishing. In other words, over the long term, that is, many billions of years, gravity will override everything. What does this mean specifically for the end of our universe? Well, there won't be any more galaxies. All the solar systems and their planets will fall into the black holes in the center of every galaxy. And all that will be left will be isolated black holes. That's the bleak end of our universe. But we can exploit gravity for space travel too, because the gravitational fields of orbiting planets are ideal for performing flyby maneuvers.
Space travel using gravity rather than fuel. Navigating a spaceship or a probe through our planetary system is an extremely complicated business, as its trajectory is affected by every mass in the system. But it's exactly these effects that are required to travel deep into space.
If you want to send a probe, for example, into the outer solar system, you don't send it directly to Pluto or wherever. You use the fact that the probe will be attracted by Jupiter, and the energy of Jupiter can be exploited, as it were, to accelerate it.
Mission planners use the flyby of celestial bodies to accelerate, slow down, and even change the trajectory of their spacecraft. Having been accelerated in this way, the probes Voyager 1 and 2 became the first man-made objects to leave our solar system and are now venturing ever deeper into the universe beyond.
You can work it out on a computer. You don't need anything more than Newton's law of gravitation and a big computer.
The European Space Agency ESA's Jupiter mission JUICE also hinges on these principles of predictable celestial mechanics. The probe, developed by the German Aerospace Center DLR, will study Jupiter and, in particular, its moons more closely. JUICE will embark on a long journey and play an important role in the search for extraterrestrial life in our solar system. It will take the probe 7 years to reach the Jupiter system and then enter its orbit. It will fly by the moons Europa, Callisto, and Ganymede, collect data, and use the gravity from the moons to perform trajectory corrections. The probe will exploit the effects of gravity for its long journey to Jupiter. By repeatedly passing by the Earth, it will acquire the necessary momentum to ultimately reach Jupiter and enter its orbit. After 3 years in orbit around the gas giant, JUICE will then leave Jupiter and head for its final destination, Ganymede. The probe will enter into polar orbit around the Jovian moon and study it from an altitude of approximately 500 kilometers. Part of its mission will be to determine whether there's a global ocean of liquid water beneath Ganymede's ice crust, a prerequisite for potential life. The probe will then gradually orbit lower and lower until it finally crashes into Ganymede's surface.
Gravitation is just one of 4 fundamental forces of nature. There's also the strong force, the electromagnetic or electrostatic force, and the weak force. These two, the strong and weak forces, only have an effect at microscopic distances, so we can ignore them at cosmological scales. The electrostatic force has the property of being both attractive and repulsive, which means that when I have a large quantity of material, these forces average out to 0. Gravitation is very different in this respect. Masses always attract, and if I have large amounts of mass, the gravitational force is correspondingly large. My small mass can't generate much gravity, but the Earth underneath me generates a really powerful gravitational force. This is why on small scales the electrostatic and gravitational forces are weak. But the opposite is true on cosmological scales where gravity is the dominant force. We saw earlier that space has a fabric, and that masses can warp this fabric. But distortions can vibrate too, so there ought to be waves. And there are. And because distortion means gravitation, there would have to be gravitational waves too. And this opens up a whole new field of research, namely gravitational wave research.
On September 14, 2015, 2 detectors in the USA simultaneously recorded a very special signal. The first ever proof of gravitational waves. It opened up a whole new window on the universe for science. It was proof that the fabric of space-time is not static, but can change. The gravitational waves traveled 1.3 billion light-years to reach Earth. They are ripples in the fabric of space caused by a cosmic cataclysm.
On September 14, 2015, they just completed a phase in which the sensitivity of the detectors had been increased. Strictly speaking, they were the last of the scientists to work on the device. They switched it into science mode, so it worked with very low noise. They left for home just 3/4 of an hour beforehand when the detectors picked up a signal, a textbook signal.
Ein Signal wie aus dem Bilderbuch.
Two black holes, one 29, the other 36 solar masses in size, smashed into each other. The collision of these two gravitational giants was the origin of the recorded signal.
The initial reaction was a bit skeptical, however, due to the fact that we've been working on this for so long. We'd always looked forward to this day with excitement and dedicated a large part of our lives to improving the detectors in order to finally detect gravitational waves for the first time. And when it finally happens, and looks just like in the simulations and presentations you've seen and given yourself, then a part of your reaction is disbelief. Is this real?
Stimmt das denn jetzt wirklich?
And once again, Einstein was right. In 1915, he gave a presentation in the Prussian Academy of Sciences where he also talked about the existence of gravitational waves.
Gravitational waves were the last of the predictions made by Einstein's general theory of relativity that was yet to be confirmed. Many other things had been proven with great precision over the years, but gravitational waves were still elusive. The fact that we've now managed to detect gravitational waves is further confirmation of how good Einstein's theory of general relativity is.
The waves were measured by the LIGO detector in the USA. The idea for gravitational wave detectors like LIGO had been described as far back as the 1960s. They measure the change in length of two laser paths. In the LIGO detector, the laser beams pass through two 4-kilometer-long vacuum tubes that are positioned at an angle of 90 degrees to one another. Mirrors at the end reflect the laser beam back to its point of origin.
Das Prinzip zur Detektion von Gravitationsfeldern.
The principle used to detect gravitational waves is relatively simple from a physics perspective. You have two long arms. You fire light into this arm, and if the length of this arm changes, the interference pattern changes. This interference pattern is very sensitive to changes in length. We're talking about absolutely minute length changes, though, just tiny fractions of the diameter of an atom. And that's what makes it difficult. You naturally have to eliminate all spurious signals. That was the biggest achievement, really.
Das war sozusagen die große Leistung.
The LIGO detector was built in the mid-1990s, but the breakthrough was only made once it was upgraded. The technology for this was supplied by GEO 600, a gravitational wave detector at the Max Planck Institute for Gravitational Physics in Hanover. GEO 600 is designed along the same lines as LIGO, just much smaller.
Our goal with this GEO 600 detector was to achieve a sensitivity similar to the other detectors. GEO 600 has an arm length of 600 meters, whereas the LIGO detectors have an arm length of 4 kilometers. So in order to achieve the same sensitivity to gravitational waves, it had to be more sensitive. This couldn't be achieved with the technology used by LIGO, though. As a result of this constraint, more advanced technology was tested and developed for the GEO 600 detector. A significant portion of the GEO 600 technologies that were developed here were then incorporated into the second-generation advanced LIGOs.
Proof of gravitational waves resulted in the Nobel Prize for 3 U.S. physicists in 2017. They represent the thousands of scientists who worked on the project and contributed to its success.
In der Gravitationswellenforschung
In the field of gravitational wave research, we're still in what's actually a good situation where there's healthy competition.
Konkurrenz ist.
Of course, everyone wants to be the best and the first, especially when it comes to such a complex and difficult undertaking. On the other hand, no one can do it on their own.
Auch so, dass keiner ohne den anderen kann.
The first direct proof of gravitational waves was a milestone in the study of the universe. Until then, scientists were reliant on electromagnetic waves, such as light or X-rays, for their observations. With the gravitational wave observatories, they now have a completely new tool at their disposal.
Für Einstein war die Sache damals.
For Einstein, it was as clear as day. There's a fabric to space. Fabric can ripple. And soon after publishing his general theory of relativity, he predicted that gravitational waves must exist. But these ripples are so tiny. They're on the scale of the diameter of an atom, which is why you need absolute calm to measure these ripples. And where can you find that? Up in space, of course. Which is why the future of gravitational wave research is in space. And that's why the European Space Agency, ESA, is planning a new project named LISA to measure such waves from up there.
There are no disturbances in space like the vibrations or thermal problems you get on Earth. This should dramatically increase the accuracy of the measurements. As a test for the European Space Observatory for Gravitational Waves, ESA's LISA Pathfinder mission launched into space in December 2015. Its objective, to evaluate technologies and detection methods. LISA Pathfinder was positioned 1.5 million kilometers from Earth at the L1 Lagrange point. L1 is a point of equilibrium between the Earth and the Sun. Here, a probe remains virtually at rest. The probe's payload is the LISA Technology Package, LTP. It consists of two free-floating test masses. Between them is a laser interferometer, which precisely measures the position, orientation, and acceleration of the two test masses. The probe surrounding them is constructed to precisely track these test masses and thus eliminate all disturbances. This ensures that the test masses are absolutely weightless. LISA Pathfinder was a major success. The disturbance suppression it achieved exceeded the stipulated requirements by a factor of 5. The actual LISA mission is planned for 2034, a gravitational wave observatory stationed in space. A configuration of 3 identically constructed probes is planned, similar to the LISA Pathfinder. The 3 probes will fly in a triangular formation at vast distances from one another. On board the master probe is a laser, whose light gets reflected by the other 2 probes. Since, like LISA Pathfinder, all 3 probes travel absolutely free of external disturbances, they can study gravitational waves by precisely measuring the distance between them. The 3 probes form an enormous triangle of light in space between the Sun and the Earth.
The 2 LIGO detectors have an arm length of 4 kilometers, and the Virgo detector has a 3-kilometer arm length. We don't have these limitations in space. In the case of LISA, the probes will form an equilateral triangle with a side length of 2.5 million kilometers, so many magnitudes larger. And this allows it to detect much, much lower frequencies as well.
It's hard to imagine the scale of LISA. A laser beam will take 8.5 seconds to cover the 2.5 million kilometers between 2 probes. The 2 reflected laser beams will then return to the master probe.
Every time you sit there and think, wow, If this is possible, why are there so many other things we can't get right? Why are there still dead zones in the cell phone network when they can pull something like this off? It's mind-blowing.
Gravitational wave research from space is an important step toward better understanding the universe. Scientists hope the LISA Observatory will detect many other events in the universe in order to better understand and classify them. Researchers are already working on new types of gravitational wave detectors on Earth, too.
The plan is to construct new infrastructure for the so-called third generation of detectors. It will all be built about 200 meters beneath the Earth in order to eliminate the disturbances on the surface. And thanks to the increased sensitivity of the third generation gravitational wave detectors, we should be able to see a whole range of other events and advance other areas of scientific research.
Andere Ereignisse sehen können, andere Wissenschaft treiben können.
The European Einstein telescope concept describes an enormous detector buried underground. A third-generation gravitational wave observatory with 10-kilometer-long arms arranged in a triangle. The scientists expect 10 times greater sensitivity thanks to the noise suppression effect of being underground. The enormous underground laboratory is to be installed approximately 200 to 300 meters beneath the Earth's surface. Its exact location has yet to be decided, however. First, the ET Pathfinder will be built in preparation for the project, a scaled-down prototype of the Einstein telescope. The mini detector is being developed at the University of Maastricht and will have an arm length of just 20 meters. This isn't sufficient to detect gravitational waves, but that isn't the objective at this stage. The test facility in Maastricht will develop and test different technologies for then equipping the final observatory. The Einstein telescope should be able to detect gravitational waves from much more distant events than has been possible until now, and thus provide new insights into the evolutionary history of the universe. Gravitational wave astronomy is coming of age.
Gravitational wave research was somewhat of a niche pursuit before they were detected and verified. But now it's becoming mainstream.
The astronomers hope that gravitational wave research will allow them to look back into the past as far as the Big Bang.
That would be amazing. If 14 billion years after the Big Bang, we could still detect the gravitational waves emitted back then. Another example of something that would be amazing to detect: every gravitational wave can be interpreted as a particle, the same way light waves can be interpreted as photons. And photons can be deflected, for instance, by mirrors. Similarly, gravitons ought to be deflected by singularities, like black holes, and we should be able to detect this too. Regardless, the main point is that the more sensitive these gravitational wave detectors become, the further into the universe we'll be able to look, and the more we'll learn in the future. In this respect, we have a completely new cosmic detector.
Gravity. It determines the geometry of space and time. While it may be the weakest of the four fundamental forces of nature at small scales, on cosmic distances, it dominates the universe. It's a mysterious force that governs everything, from the Big Bang, the beginning of space and time, to our own existence. Understanding it completely is the key to our universe. Are we alone? A question we ask ourselves every time we gaze deep into the endlessness of space. And the dream of discovering the origins of humankind is as old as civilization itself. Are there other worlds that support life? Or is life on Earth merely a cosmic accident?
What in fact is life? What forms of life are there? And what constitutes higher intelligence? And most importantly, what are the prerequisites for the emergence of life? We naturally need solid ground under our feet. That's a planet with an atmosphere and the right temperature. But the question is, how many Earth-like planets are there out there? Or is the Earth unique? And crucially, if there are a lot of Earth-like planets, how likely is it that higher forms of life evolve on them?
Just a few decades ago, scientists believed our solar system was unique. But it turns out to be just one of many. It's now clear that pretty much every star has a planetary system, and an increasing number of these extrasolar planets turn out to be rocky planets that are at least similar to Earth.
If there are planetary systems elsewhere, the natural question is one of them similar to ours? Does it have a second Earth? And if so, is it home to life similar to us?
Planetary systems are seemingly the norm in the universe. It appears that whenever stars form, planets do too.
I consider the likelihood of Earth being the only place life has developed in such a vast cosmos to be fairly small, because the conditions necessary for life seem to be present in many regions of the universe. The requirements for life as we know it are liquid water, energy, and a particular chemical composition, that is carbon and a few minerals. These are the three things you need to create biological life as we know it.
3/4 of our planet are covered by water, the prerequisite for all that we consider to be and recognize as life.
There's more or less a consensus on the key characteristics, and these naturally include the metabolism. From a thermodynamic perspective, life is an open system, which means it's continually exchanging chemicals and energy with the environment. Important key characteristics include growth, reproduction, and of course the ability to adapt, which may result in a survival advantage.
The Earth teems with life in a myriad of forms and varieties. But how life on Earth actually got started is one of the great mysteries.
The origin of life on Earth is still an unresolved issue. We know that there was primitive life on the Earth around 3.5 to 3.7 billion years ago, in the form of anaerobic bacteria that had to live without oxygen. They're very simple life forms, but even getting to this point is incredibly difficult.
From the time life began to evolve on Earth around 4 billion years ago, it took another roughly 500 million years before the first primitive, oxygen-producing life forms appeared. And it was only after a further 3 billion years that a huge diversity of species arose. This epoch has lasted for approximately 540 million years and continues to this day. Our solar system formed from a pre-solar nebula of hydrogen and dust following a supernova. Gravitational forces caused this cloud to collapse in on itself, a rotating cloud of dust and gas from which the Sun formed 4.5 billion years ago. The planets form in orbit around the Sun. The primordial Earth is a ball of molten rock enveloped in a toxic atmosphere. As it cools, the Earth's crust forms. Water vapor condenses and the oceans are formed. But how life was able to emerge from this inanimate matter remains a mystery to this day.
The still unresolved question is, how is it possible that back then, 600 million years after the formation of the Earth, inanimate matter, basically rocks, gave rise to complex biological life? We still don't know today, but what we do know is how the first precursors, namely organic molecules such as amino acids, formed, as there's a very interesting experiment we can do to create them.
In 1953, Stanley Miller tried to recreate the origins of life. In the laboratory of Nobel Prize winner Harold Urey, the young chemist mixed together the substances thought to have constituted the primordial atmosphere and oceans of the early Earth.
He took some carbon, liquid water, irradiated it with energy in the form of sparks, so electrical energy in this case. He heated it up a bit and added a few other inorganic compounds, in the hope of generating amino acids, which are the building blocks of life.
Miller's experiment was an attempt at simulating abiogenesis, and after just a few attempts, organic compounds were created in the mixture, including various amino acids, the building blocks of life.
Die Miller-Urey-Experimente
The Miller-Urey experiments were based on the assumption prevailing at that time that the primordial atmosphere contained a large amount of ammonia and methane, and organic molecules can be generated from them via electrical discharges. Today, however, we know that the atmosphere probably contained very little ammonia and methane, and was composed mainly of nitrogen with some carbon dioxide.
Miller's experiment didn't solve the mystery, but under primordial conditions it was possible for all the key parts of ribonucleic acid, or RNA for short, to be created, a precursor of DNA.
RNA is not only an enzyme. It can store information too, and plays a crucial role in the synthesis of protein in the cell. It's basically involved in synthesizing all of the proteins in a cell. It's an autocatalytic active molecule, but it should be mentioned that it's naturally assembled from other parts, namely sugars, phosphates, and nucleotides. All of these are organic and inorganic molecules that first have to have formed and come together. So there's actually another preliminary stage here.
Das heißt, da gibt es wirklich noch eine Vorstufe.
The first living cells may have formed around 4 billion years ago in deep cracks in the continental crusts, tectonic fracture zones that connect the Earth's mantle with the surface, and in which gases and liquids circulate. Hydrothermal conditions prevail in these fissures, where the pressure is so high that water can remain liquid at temperatures far in excess of 100 degrees Celsius, and thus contain large amounts of dissolved gases and minerals, favorable conditions for the formation of life.
Leben zu erzeugen und zu entwickeln.
In order for life to form and evolve, it requires raw materials. But there was little inorganic material available, and only a few organic molecules on the early Earth. So we need a source of these raw materials. And naturally, there were places on the primordial Earth, like volcanic regions, lakes, and hydrothermal vents in the deep ocean, where organic compounds may have formed.
In this way, the first cells could have formed on land, too. In this case, the necessary building blocks would have been supplied by hot springs and pools in volcanic regions.
But there's actually a second source, namely space. Because during its first 700 million years, the primordial Earth was regularly bombarded by asteroids, comets, and smaller objects, which brought materials such as water and even organic molecules to the early Earth. And we know from the composition of these small objects that they contain prebiotic molecules too.
But even if the building blocks of life, or even simple organisms, arrived on the primordial Earth from outer space, it still doesn't explain how life can come about in the first place. It just shifts the mystery into the depths of space.
What are the prerequisites for life? Well, let's take a look using our planetary system. First, we need a solid planet. So we can disregard all the gas planets beyond Jupiter. That leaves us with just 4 possible candidates. We also need the temperature to lie between 0 and 50 degrees Celsius. And that equates to a very particular distance from our sun, which is pretty much here. So Mercury is disqualified. It's far too hot. Venus lies on the innermost edge, but because its atmosphere is composed mainly of CO2, a runaway greenhouse effect means a temperature between 400 and 500 degrees Celsius. The Earth lies right in the middle. No CO2 atmosphere, ideal temperature. And Mars lies just outside. It has no atmosphere to speak of anymore and is unfortunately too cold as a result, namely between minus 150 and 0 degrees Celsius.
Of all the planets in our solar system, Venus is closest to Earth. Its size and mass are similar to that of the Earth, too. For a long time, scientists speculated about the existence of life on our planetary neighbor. But having been visited by several probes, the interest has waned. Most scientists now doubt the existence of life on Venus. With surface temperatures well above 400 degrees Celsius, a toxic atmosphere, and pressures similar to those in the deep sea, Venus appears to be hostile to life.
Evidence of life will always be circumstantial. If an alien is standing in front of us, waving like in a Hollywood film, something I consider highly improbable, we might be certain. But otherwise, evidence for primitive life will always be circumstantial. This means we have to exclude all other possibilities. And that's what makes it so difficult to say when we really have discovered life.
The search for extraterrestrial life in our solar system is focused primarily on Mars. It seems certain that it once had a completely different climate to the one it has today. Approximately 3.5 billion years ago, around the time life formed on Earth, it was for a time at least warm and wet there. Back then, Mars presumably had oceans that subsequently disappeared. Today, water exists in the form of ice at the poles and probably in seas below the surface.
Mars is very interesting because it's a relatively large planet. In the past, the conditions on Mars in terms of atmosphere, temperature, and so on were quite similar to those on Earth. But we don't see any Martians strolling around there today. So was it home to life or not? And why is there life on Earth? It's possible that Mars can help shed some light on the matter, which is why our ExoMars mission is designed to look specifically for life on Mars. It's exciting. It's possible that there still is, or was, something akin to life, not on the surface, but perhaps in the Martian interior.
In 2018, the ESA probe Mars Express discovered liquid water beneath the ice at the South Polar region. A whole system of ancient lakes may exist there, maybe millions or even billions of years old. Ideal locations to search for life.
There are riverbeds there, and the conditions in the past were very different to those today. So it's possible that life existed there at some time. Finding the traces today is no easy task, though. A great deal of time has probably passed since then. If there are traces, I would assume they are to be found where there's still water, namely at the poles.
Mars' gravity is too weak to hold on to liquid water and an appreciable atmosphere on a permanent basis. And even though Mars may have looked very different at one time, the conditions there have never been sufficient to support higher forms of life.
What are the prerequisites for higher life forms to evolve in the universe? Well, first, we need a proper star, like our Sun. If the star were larger, it would be much too hot and emit radiation in the so-called UV and X-ray regions, which is detrimental to biological life like ours. If the star were smaller than our Sun, it would be a so-called red dwarf. And that's not good either, as they have the unpleasant habit of emitting X-ray flares, and X-rays are not biology-friendly. And then you need a proper planet, of course, where proper means a rocky planet you can stand on, like the Earth or Mars. But it can't be too big or small either. If it's too small, like Mars, it can't hold on to an atmosphere, which we need. And if it were too large, its gravity would be too strong for organisms to grow large, which we also need for them to develop large brains and become intelligent. What else do we need? Well, we need a large moon. Because, as we've learned from our moon, large moons stabilize the axis of rotation of a planet, and we need that for the climate to remain stable. Only under these conditions can higher life forms evolve. And we need a giant, a large gas planet like Jupiter, because, as we know, gas giants protect us from asteroid impacts. But it doesn't have to be a planet. In principle, any suitably large moon would do as well.
Which is why the icy moons of Saturn and Jupiter have also come under the scrutiny of scientists in their search for life. The researchers believe that life is possible under their thick ice crusts. Probes have discovered vast oceans beneath the ice sheets. The scientists suspect that there are oceans on the distant moons up to 100 kilometers deep, kept liquid by the gravitational pull of the two giant planets.
Also man hat flüssiges Wasser und eine Energiequelle.
So you have liquid water and an energy source. These moons are almost certainly composed of the same material as the Earth and all the other rocky planets. In other words, they'll have carbon and minerals inside them. Minerals, carbon, energy, liquid water. These are the building blocks of life. And there's even an ice crust that protects the interior against cosmic radiation. And bearing in mind that life on Earth evidently formed in water under very extreme conditions, the hope is that the same sort of thing took place in these oceans as occurred on the early Earth.
Sich möglicherweise das Gleiche abgespielt hat, was sich abgespielt hat auf der frühen Erde.
Studying Jupiter, and in particular 3 of its largest moons, is the objective of the European JUICE mission. JUICE, the Jupiter Icy Moons Explorer, should provide us with new insights into the water-rich moons Callisto, Europa, and Ganymede. The probe will take 7 years to fly from the Earth to the Jovian system, which it will spend several years investigating. At the end of its journey in 2032, JUICE will enter into orbit around Ganymede, from where it will analyze the moon. With a diameter of 5,262 kilometers, it's the largest moon in our planetary system. Ganymede has a magnetic field and, even though very thin, an oxygen atmosphere.
Ganymede, muss man sich vorstellen, ist ein riesengroßer Mond.
Ganymede is a huge moon, much bigger than our moon. If it didn't happen to be orbiting Jupiter, it would be classified as a planet because it's so big. It has a diameter of around 5,300 kilometers, so it's really huge. That's almost the size of Mars. So it's a very large moon, and that's what makes it so interesting. We think that the conditions there may be conducive to something like life. It could be that we discover something amazing there.
Another candidate for life is Saturn's moon Enceladus. Its surface is made of pristine white snow. Although it picks up dust on its journey through space, it doesn't appear dirty. The fresh snow is produced by water that continually erupts from its surface and crystallizes.
Liquid water is a prerequisite for life. So if there's liquid water beneath the ice crust and an energy source, like tidal forces that deform the moon, then it fulfills the conditions that could theoretically allow life to form. There's hope to find proof on Saturn's moon Enceladus, where geysers have been discovered. That means water from the ocean that shoots out into space through cracks in the surface and vaporize. So the hope is that an analysis of this material will provide clues as to the composition of the water in the ocean. And if we're lucky, perhaps we'll find organic compounds in it.
The geysers on Enceladus were discovered by the Cassini-Huygens mission. The two coupled probes were given the job to study Saturn and its moon. Huygens was designed as a lander. Its destination, Titan.
Another interesting object in our solar system is the Saturnian moon Titan, and for several reasons. First, it's the only moon with an atmosphere which consists mainly of nitrogen. It's the only moon which has liquid on its surface. In this case, liquid hydrocarbons, primarily methane. Methane does there what water does here on Earth. It has a solid surface, and it appears to have a kind of cycle too, of hydrocarbons. On Earth, we have a water cycle where it rains. The water soaks into the ground, evaporates and forms clouds again, creating a water cycle that's critical for life on Earth. There seems to be a similar cycle on Titan, but involving methane and other hydrocarbons. It would be extremely interesting to take a spoonful of liquid from one of these methane lakes and analyze it.
In January 2005, Huygens began its descent to the surface of Titan. The images show a barren world with rivers and lakes of methane. And it's possible that this hydrocarbon could somehow have given rise to some form of primitive life. The moons in our planetary system appear to be good candidates for extraterrestrial life.
I reckon Enceladus will be the first place we discover life. We'll send a probe through these water plumes that have formed along the ice fissures and extend kilometers into space. An element analysis may show amino acids, more complex compounds, and even organic material. And then we'll conclude that this moon is home to primitive life. That's my prediction, that it'll be where we discover extraterrestrial life first.
The search for life is one of our biggest and probably most exciting scientific endeavors. And since the first planet outside our solar system was discovered in 1995, the search for a new world has captured our collective imagination.
Do exoplanets actually exist? That is, planets in other solar systems. Today, the answer is clear. The discovery of another exoplanet is announced on an almost daily basis. We now know of many thousands of exoplanets, but it's actually not that long since the first one was discovered. And we now know why every star has not just one planet, but must have many, because they contain the initial rotation of the entire planetary system. They contain the so-called angular momentum. The key question, however, is how many of these planets are Earth-like, and in particular, are as large as the Earth so that life can develop on them. And we now know there aren't really that many of them.
One particularly fascinating planetary system is TRAPPIST-1. Its central star, TRAPPIST-1a, was only discovered in 1999. 7 rocky planets orbit the star, which is 40 light-years away. In terms of their mass and diameter, these planets are comparable to the Earth. And the conditions on a few of them may even be hospitable to life.
The TRAPPIST-1 system is interesting because it has 7 small planets, and 2 of them are at a distance from their star that could allow water on the surface to exist in liquid form. We would consider them potentially habitable, if it actually were there. We haven't detected water yet, but they're situated at the right distance for it.
The 7 rocky planets that orbit the dwarf star TRAPPIST-1a fascinate scientists. But above each planet hovers a big question mark as well. Their size and density can be reliably determined, but whether the TRAPPIST-1 planets actually have an atmosphere or even oceans of water is still unknown. Scientists presume they do, but their assumptions are based solely on models thus far.
Getting observational evidence is difficult for the TRAPPIST system too. So we're still looking for a system that's Earth-like, or rather Earth-Sun-like, where we can confirm the atmosphere of an Earth-like planet with certainty.
In order to study exoplanets and, if present, their atmospheres in more detail, the scientists are using the latest generation of telescopes. Nonetheless, even these will not make it possible to observe details on their surfaces directly. The distances are simply too great.
You can't simply point a giant telescope at the planet and look at it. At the moment, you have to rely on chemical signatures. That is, you look for water. You look for evidence of water. And some, using clever techniques, the astronomers have succeeded in detecting water on such planets for the first time. They are, of course, tiny signals, and if there's water, we conclude there could be life too.
There's now certainty that our solar system is not an exceptional case, and the formation of planets is a perfectly normal process in the universe. Scientists have identified thousands of exoplanets so far, and they describe many of them as Earth-like. The closest extrasolar planets discovered thus far orbit the star Proxima Centauri, around 4.2 light-years away.
The problem is that Proxima Centauri is a star that has less mass than the Sun and is not so stable. This means that if you were on a planet there, you'd have to reckon with being regularly blasted with UV radiation, which isn't so good for living organisms. You'd get pretty sunburnt there. But still, it's just 4 light-years away. And 4 light-years is a distance you could potentially span with a probe sometime in the future.
The exoplanet Proxima Centauri b was discovered in August 2016 from Earth by the European Southern Observatory ESO. An Earth-sized rocky planet that orbits within the habitable zone of the red dwarf and could, theoretically at least, harbor life. A second planet in the system outside the habitable zone was then discovered in 2019, Proxima Centauri c.
So, how do we find exoplanets? It's actually pretty difficult, because planets are extremely dim, whereas the central star is so bright, it dominates everything else. For that reason, we can never observe planets directly. But there are a few tricks we can use, and the best known is the so-called transit method. How does it work? If we look at a star from Earth, it can happen that the planet passes in front of the disk. And when this happens, it obscures a tiny part of the disk, and the star's brightness reduces very slightly. Using modern detectors, we can measure this drop very precisely. Better yet, just before the planet enters the disk, the light from the star is only obscured by the planet's atmosphere. And when this happens, we can measure the concentration and composition of the atmosphere fairly precisely. But this still doesn't answer the question, is there life on an exoplanet like that?
Every star in our universe has its own system of planets. This much seems certain. And our galaxy alone contains an estimated 100 to 400 billion stars. But are there other worlds out there that harbor life? In the search for extrasolar planets, we have one major goal. We're looking for a celestial body that has similar properties to our home planet. The ideal planet should be orbiting a star of a similar size and age to our Sun. It should be roughly the same size as the Earth and be at a favorable distance within the habitable zone of its star. The German aerospace center DLR is also searching for such a planet. Its space telescope Plato has the mission to find rocky planets the size of the Earth that are orbiting nearby Sun-like stars.
Plato will observe two regions. The cameras allow us to observe a very large portion of the sky, as they're divided into 4 groups whose lines of sight are slightly offset with respect to one another, giving us a wide field of view. We'll survey a region for at least 2 years, because we want to discover planets that have an orbitable period of up to a year. As such, we have to observe for at least 1 year, in order to discover a transit. And once we have a possible candidate, we'll then begin the Earth-based program, which involves radial velocity measurements to determine the masses.
For the Earth-based observation program, a brand new, powerful planet hunter is currently under construction. The ELT, the extremely large telescope of the European Southern Observatory ESO. The super telescope is located in the dry and near cloudless Atacama Desert in Chile. With its 39-meter mirror, it will operate in the optical and infrared region of the spectrum and be capable of discovering and observing exoplanets directly. It will also study their atmospheres, temperatures, and seasonal weather conditions. The atmospheres of the distant planets in particular would provide evidence of the possible existence of life. The scientists are looking for so-called biomarkers, molecules that are produced by living organisms like microbes and algae, which then accumulate in the atmosphere.
The way we'll discover life for the first time will be by finding an atmosphere with maybe oxygen, a bit of carbon dioxide and methane, and we'll conclude that there must be an oxygen producer, and oxygen must be continuously being replenished. And that can only really be achieved by biological life as we know it.
There are countless planets in our universe, but scientists are yet to find one that fulfills all the conditions necessary for life. And even if we do find such a planet, we cannot be certain that life, perhaps even higher forms of life, has developed.
Carbon, energy, a few minerals, liquid water. And bam! Does life always develop on a planet under these circumstances? Or is it actually the result of a series of random events, so that here on Earth we just got really lucky? This naturally begs the question, how much life is there in the universe? This is the fundamental scientific question. Is there a process that inevitably leads in this direction?
Scientists are also searching for the possible origins of life in the seemingly empty regions of space between the stars and planetary systems. Complex molecules exist everywhere in the universe, including the exact same molecules that served as the basis for life on Earth. They're found in the huge interstellar clouds of gas and dust from which new stars are born. There, minute dust particles repeatedly collide with individual atoms and can, over millions of years, combine to create ever more complex molecules.
Molecules are formed in many regions, but most notably in the interstellar clouds, the regions between the stars. And we've now discovered over 200 really important molecules there. And another 4 or 5 are discovered each year. These molecules are mainly discovered using radio telescopes. And it's very exciting, of course.
The first ever molecule to form in the universe shortly after the Big Bang was detected in 2019 by the Flying Observatory SOFIA. Helium hydride. Shortly after the Big Bang, a few very light elements were produced, including hydrogen and helium. And it's from these two elements that the first molecule formed.
As the universe cooled, this molecule could combine with hydrogen to produce molecular hydrogen. And this is really important, because it more or less formed the basis of the first large stars in the universe.
The very first helium hydride molecules formed over 13 billion years ago. It marked the beginning of chemistry in the cosmos. This latest discovery is evidence of nature's tendency to form molecules.
SOFIA isn't specifically looking for extraterrestrial life forms. Rather, we're looking for chemical indicators and organic molecules. And we're finding them. There are a lot of organic molecules in space, like acetic acid, alcohol, and so on. In the far infrared and radio spectrum in particular, many of which are unknown. We also see a lot of spectra that indicate the presence of molecules that are new to science, or haven't been identified yet.
Despite the harsh conditions in space, ever more complex molecules are being discovered. By studying molecule formation in the interstellar medium, scientists hope to learn more about how life formed on Earth.
What will extraterrestrial life look like? Little green men or aliens with enormous heads? It's actually quite simple. Primitive life, that is, single-celled organisms, will almost certainly be around. When it comes to higher life forms, it depends on whether they can move or not. Trees can't move, which is why they're rotationally symmetric. If something can move, it always has a plane of symmetry, and its body is then mirror symmetric. And that's exactly what we expect extraterrestrial life to be like. But if we find a planet that actually does have life on it, we expect it to be inhabited by so-called extremophiles. These are organisms that have adapted to extreme environmental conditions, such as high temperatures, extreme aridity, or can withstand cosmic radiation.
Whether or not terrestrial extremophile organisms can survive the inhospitable conditions of space is being investigated on ISS-2. On the space station, bacteria, algae, lichens, and fungi are being exposed to the vacuum of space for extended periods of time, and some of them return to Earth unscathed. Tardigrades are true masters of survival. Barely a millimeter in size, these creatures live in mosses and have to cope with extreme changes in the conditions, from wet to totally dry.
Tardigrades are able to completely dry out or freeze solid, and when the environmental conditions improve again, that is, when it gets wetter or warmer, they rehydrate or thaw out and go searching for food once more.
The TARDIS project, Tardigrades in Space, involved sending tardigrades on a trip to space. In their dried-up, suspended animation form known as their ton state, they spent 10 days in Earth's orbit exposed to the conditions in space. The majority of the moss and water dwellers survived the vacuum unscathed. Some of the animals were exposed to the hostile cosmic radiation. 2% survived even that.
What prompted this experiment are the incredible capabilities of the tardigrades. Their resilience to drought, cold, and above all, cosmic and other forms of radiation. And the idea of this experiment was to see how the tardigrades, as living organisms, could cope with the harsh conditions in space. At the end of the experiment, the tardigrades returned to Earth, and we examined how well they survived their trip to space.
Zurück zur Erde und wir haben uns angeschaut, wie haben sie diesen Weltraumausflug überstanden.
Astrobiologists expect that extraterrestrial life could possibly look like this, or similar. At any rate, it has been demonstrated that certain organisms are able to survive unprotected in space.
Tardigrades sind wirklich ganz putzige Tierchen.
Tardigrades are really cute little creatures, especially when you observe them after they come back from a trip to space and you rehydrate them. And they just pick up where they left off and continue their life cycle as if nothing has happened. It's certainly interesting. And we're finding more and more exotic life forms on Earth. There's a great deal we still don't know about our own planet. In mines in South Africa, for example, we're discovering organisms deep inside the Earth where we never thought it possible for life to exist. We're continually finding new exotic forms of life here on Earth. So we're still learning about living organisms on our own planet. This means that there may be forms of life in our solar system and even on extrasolar planets that we can't imagine today.
Geben könnte, die wir uns heute noch nicht vorstellen können.
In April 2019, a private Israeli space probe smashed into the moon. On board the crashed lander were several thousand tardigrades in their dried-out state. So now, there's life on the moon, albeit in a state of suspended animation.
Life in space? Why look for it? Maybe they're already trying to contact us. It was with this in mind that in 1961, the first conference on the search for extraterrestrial signals was held, the so-called SETI. There are many such projects nowadays, but for a long time, nothing was detected. Until in 1977, a highly unusual signal was recorded, the so-called WOW signal. Why was it called WOW signal? Well, after over 10 years of searching, a researcher came in one morning and looked over the printout from the previous night and saw this huge signal and was so overwhelmed, he wrote beside it, WOW.
The so-called WOW signal is a narrow-band radio signal from outer space that was significantly stronger than the background noise. The unusual signal was received on August 15, 1977 by the Big Ear radio telescope at Ohio State University. It was recorded by astrophysicist Jerry Eman as part of the SETI project. SETI refers to the search for extraterrestrial intelligence. In the early 1960s, astronomer Frank Drake, using the Green Bank radio telescope, became the first person to look for signals and messages from outer space. The SETI project was born, but no message has been received to this day. And the WOW signal was presumably the result of a burst of gamma rays.
Dass man Funksignale auffängt, da muss man wahrscheinlich noch ein bisschen Glück haben.
You probably need a fair bit of luck to intercept a radio signal. There are two problems here. Problem number one, the others are a long way away, so the radio signal that arrives here is extremely weak. Problem number two, it has to be sent at the right time as well. Imagine that, say, 10 million years ago, the aliens sent radio signals in our direction for 1 million years. Unfortunately, we weren't in a position to receive them back then. So you have to send the radio signal at the right time. And maybe these aliens only survived for 1 million years and then somehow destroyed themselves, something mankind can relate to. It could also happen to us, that we destroy ourselves. So the time has to be right. Transmitters and receivers have to be in a position to send and receive at exactly the right time.
The researchers have now been looking for signals from an alien civilization for over half a century, without success. Surely billions of Earth-like planets should provide ample opportunities for intelligent life to evolve.
Intelligentes Leben.
Intelligent life is really a whole new dimension. If we consider how life has evolved on Earth, we see that microbes have been around for 4.5 billion years. But humans have only been around for 2 million so far. We don't know how long it will go on for. And if we consider the complexity in the evolution from primitive bacteria to human beings, there's a vast number of intermediate stages involved. It's incredibly difficult to imagine that these intermediate stages could actually occur in exactly the same way on another planet in our universe. But you have to keep an open mind, and it's quite possible that intelligent life has evolved elsewhere in the universe, maybe even under different conditions.
The emergence of intelligent life is tremendously complex, but the sheer endless number of distant planets alone is a strong argument for intelligent life existing, or having existed, somewhere else in the universe. When and for how long it existed, or whether it's only now evolving, and where in the cosmos it may be, these are unanswerable questions.
It's basically true to say that the universe could be relatively densely populated, as it were, and we may still be unable to detect the others. Imagine the following scenario. There's a planet about the size of the Earth, and it's called Kepler 452b. It takes 384 days to orbit its star, which is about the same size as the Sun. The difference between this planet and our Earth is that it's 1.5 billion years older. If people lived there, they may have been broadcasting messages hundreds of millions of years ago. But the dinosaurs on Earth weren't able to receive them yet. And a few 100 million years later, they couldn't transmit any more because all their resources were used up or something. So now that we're able to receive, they can't send anymore.
Humankind has only been broadcasting signals into space for a little over 100 years. Distance and time are key factors that cannot be influenced when it comes to the search for signals from outer space.
We can also turn the question around. What could aliens discover about us? Well, they would spectroscopically analyze our atmosphere and say, wow, that's a weird atmosphere. Then they try to detect electromagnetic waves, which they'd succeed in as we generate them artificially, for instance, for our TV broadcasts. They may even be able to watch our programs with very sensitive detectors, so when you think about it, some of those programming directors should perhaps reconsider what they broadcast. Because our television programs are the first thing the aliens will discover about us, since they're transmitted at high power.
As long ago as 1950, physicist Enrico Fermi asked his colleagues over lunch, "Where are they?" What he meant was the spacefaring aliens who, assuming they existed, should have visited Earth long ago. The conclusion? Since they aren't here, there can't be another technologically advanced, intelligent species in our galaxy.
We have, in the meantime, broadcast messages deep into the universe in the hope that extraterrestrials might receive them, but no response so far. So, where are they? Well, it could be that we're the only ones in our galaxy, the Milky Way. Perhaps even in the whole universe. Or will we meet them when we travel to other stars sometime in the future? It can't be ruled out, but seems pretty unlikely, as so far there's only been resounding silence. Primitive life may nonetheless exist, and if it does, we'll find it.
At present, we know of just one celestial body where life exists, our planet Earth. And scientists are faced with a mystery. They still don't know how inanimate material can give rise to life in the first place. But the necessary building blocks apparently exist throughout the entire cosmos. And there's one thing about which the scientists are certain. The discovery of life, though most likely in a primitive form, in our planetary system or galaxy is just a matter of time. Since the dawn of time, the moon has been our faithful celestial companion. But other planets have satellites too, and often more than the Earth. The silent companions of the planets are fascinating worlds in their own right, and some may even be candidates for extraterrestrial life.
At first sight, moons seem like a pretty simple affair. Moons orbit planets, and each planet has at least one of them. But in fact, things aren't quite that straightforward. Incidentally, people in earlier centuries were far more poetic. Kepler, for instance, reckoned that moons are there to provide the inhabitants of the planets with light at night and afford them the spectacle of their rising and setting. That's how people thought back then. Today, we think that in the future the moons will provide us with raw materials and serve as a base for colonies. But what interests us today is, what actually are moons? How did they form? And could they even be home to primitive life?
Everything in the universe is in motion. The Milky Way revolves around its center, and with it, our sun. The planets orbit the sun. Moons accompany those celestial bodies that orbit a star. This is why moons are also referred to as satellites, which means companion. We haven't yet discovered life on any moons, but then again, we've only actually investigated a handful so far. The Earth's moon was visited by the Apollo astronauts. A probe has landed on the Saturnian moon Titan. Of all the others, we have only photos taken through telescopes or by passing space probes. High time we explored those moons more thoroughly. Not all moons are alike, quite the contrary. Ganymede is frozen and huge, bigger than the planet Mercury, in fact. Titan has a dense atmosphere and landscapes with mountains, rivers, and lakes similar to the Earth. Io is as colorful as a pizza and covered by active volcanoes. Enceladus is only medium-sized, looks like a ball of ice, and ejects icy plumes out into space. But it's a sphere, at least.
The moons of our solar system, especially the ice moons, are some of the most fascinating objects in our solar system, and especially since we discovered signs that there may be oceans beneath their frozen surfaces.
It isn't proven, but neither can it be ruled out that life may well have arisen in the oceans of some of these moons.
In order to be as spherical as our moon, a moon must accumulate quite a lot of material during its formation. Otherwise, it won't have sufficient gravity to form a sphere. Only a few moons had this much mass during their formation. The smaller the moon, the more irregular its shape. The Martian moon Deimos, for example, is tiny and looks like a potato. But planets aren't the only bodies that have moons. Many dwarf planets and even asteroids have them. With their modern instruments, researchers have discovered several hundred moons in our solar system that orbit planets and asteroids.
So how did all the planets and their moons form all those eons ago? Well, let's take a look at the situation 4.6 billion years ago. This is it. There was a rotating disk composed primarily of hydrogen gas and dust particles. These dust particles collided with one another and formed even larger objects we call planetoids. There were larger and smaller planetoids, and dust disks around these planetoids. And it's from these dust disks that the moons formed. Another thing that happened was that the larger planetoids captured the smaller ones. Other moons formed in this way. Right at the end, the following happened to Earth. As the planets had already formed, a relatively large planet, roughly the size of Mars, smashed into our Earth. And this is probably how our moon came into being.
Theia. This is what astronomers christened the planetoid that hit the Earth in the early days of the solar system. It must have been a spectacular event. This collision created the Earth and the Moon, which then cooled down over the space of several billion years to become the objects we know today. That's the generally accepted hypothesis.
I think all of my colleagues agree that there was a massive collision between the Earth and another object the size of Mars. Not head-on, more of a glancing blow. The Earth was ripped open and a great deal of material was ejected from the Earth into orbit, where it coalesced to form the Moon.
The Moon is the celestial body that is closest to us, and the one we are most familiar with. Since the dawn of mankind, people have gazed up at the Moon. It has always fascinated them. The Nebra sky disk, which was found in Saxony-Anhalt in Germany, was made by Bronze Age people around 4,000 years ago. The full moon and the waxing moon are the most prominent elements. As if people back then realized the fundamental importance of the Moon for life on Earth, namely, due to its gravity.
For one thing, it guarantees our seasons. The seasons are a consequence of the Earth's axis being tilted by around 23 degrees. The Moon orbits the Earth and stabilizes this axis. If the Moon weren't there, its axis would slowly tip over and there would be times when we'd have no seasons at all. So the Moon ensures that we enjoy relatively stable conditions.
It stabilizes our axis, which would otherwise wobble around a bit as it gets pulled by Jupiter and then by the Sun. But the Moon acts a bit like an outrigger on a canoe, and is why our climate actually remains fairly constant.
The Moon is also responsible for the tides. Who knows whether there would be life on Earth at all without the ebb and flood? The intertidal zones in particular provide ideal conditions for it. And it's presumably from these shallow zones, sometimes flooded, sometimes dry, that the first life forms crawled out of the sea and onto land.
The intertidal zones are replete with the nutrients required for life, so it's probably where life actually first arose. And without the Moon, these large movements of water wouldn't have happened, and life may not have developed.
The Moon, with its phases, is the clock by which our calendars are set, and where the word month comes from. A month originally designated the time it takes the Moon to go through all phases, from one new moon to the next, in around 29.5 days. The Moon regulates life on Earth, as it were.
The repeating, regular, cyclical events, they all have something to do with the Moon. As such, it has a big influence on our experience of reality, the order of events. Apart from the years, it demarcates time. And for me, that all makes it a trusty companion I love to look at. I'm always reminded of the song by Matthias Claudius, Der Mond ist aufgegangen, or The Moon has risen.
The Moon is the only extraterrestrial body that humans have set foot on to date. When the Apollo astronauts from the USA flew to the Moon 50 years ago, it was not so much out of a desire to explore. It was primarily to show the Soviet Union who was ahead in the space race. But they nonetheless brought back a large quantity of Moon rocks, the analysis of which revolutionized our knowledge about the Moon. It's only since probes and astronauts have circled the Moon that we know that the front and backside are completely different. The front is characterized by large, dark patches, huge lava plains. We don't find them on the backside. It consists mostly of elevated plateaus full of impact craters. The fact that it's like this is related to how the moon was formed. Perhaps future astronauts will shed more light on the matter when humans return to the moon. NASA's preparations for this are already at an advanced stage. They intend to use the moon as a staging post for journeying deeper into space.
The Americans have this program they're now calling Artemis, the twin sister of Apollo, among other things, to indicate that this time female astronauts will fly to the moon too. This Artemis program encompasses a whole range of different concepts. There's the Lunar Gateway, a kind of bus stop orbiting close to the moon from where it's easy to descend to the lunar surface, and that can only be used as a staging post. It's a big program, and NASA naturally imagines it being the stepping stone to Mars.
At present, the International Space Station is the most important multinational space program. The European Space Agency, ESA, can imagine a base on the moon, the so-called Moon Village, as its successor.
I think a good way to imagine the Moon Village would be using the analogy of an Antarctic research station. That gives you an idea, but it goes beyond that. The Moon Village concept is much more extensive. It can allow for things like developing technologies relating to energy provision, for example, and even tourism. Who knows? So the concept of the Moon Village is explicitly being kept open. It should remain open for different purposes for technicians and, of course, scientists and researchers.
But is it really worth flying to the moon? Except perhaps for research purposes? The mining of helium-3, a possible future source of energy, for instance, would be extremely costly.
The moon is a bit like an extra continent, and I'm sure we'll at least use it sooner or later. But whether we really will permanently settle there, there are a great many difficulties in doing this. But we will fly there again, I'm pretty sure of that. Apollo showed that a 3-day outward journey, 3 days there and 3 days back again, worked perfectly. And 100 years ago, you couldn't even get from England to America in 3 days. But I'm sure that when there's a base on the moon that can comfortably accommodate people for 3 days, tourism would be an option. I mean, if you actually had a shuttle to the moon and said we'll be able to fly there in 10 years, I reckon it could already be sold out today.
We haven't known for all that long that there are other moons out there besides our own. In 1610, the Italian scholar Galileo Galilei pointed his home-built telescope at the planet Jupiter. He discovered that this planet had 4 companions.
It was an earth-shattering discovery that these moons behave the same way with respect to Jupiter as the planets do with respect to the Sun.
In this way, Galileo indirectly confirmed the heliocentric worldview, with the Sun in the center instead of the Earth. Io, Europa, Ganymede, and Callisto. The Galilean moons are named after lovers of the Roman god Jupiter. Hundreds of other moons have been discovered since Galileo's time. We now know of 79 Jovian, 82 Saturnian, 27 Uranian, and 14 Neptunian moons. The inner rocky planets, Mercury, Venus, Earth, and Mars, on the other hand, only have 3 moons between them, our own and 2 that belong to Mars. Which raises the question, why is this?
Why do Mercury and Venus have no moon? The Earth just one, and all the other planets out there more. Even the dwarf planet Pluto has 5 moons. Why is this? Well, it's a question of a moon's orbital stability. I should explain that in more detail. Let's assume we have the Sun here. And a planet here. This is the line connecting them. Now we'll take a random point in between, say here. The question is, how much stronger is the pull exerted by the planet compared to the pull exerted by the sun? Here, the pull of the planet is greater, so the moon feels attracted to the planet. If I take this point, the opposite is true. The pull toward the planet is less than toward the sun. So somewhere in between is a boundary which defines a sphere within which moon orbits are stable. This is called the Hill sphere. Now here's the thing. The closer a planet is to the sun, the smaller the Hill sphere is, because the gravitational force of the sun increases. So Venus has a very small Hill sphere, which is why it's very unlikely that Venus has a moon. The same is true for Mercury. But the further out I go, the bigger the Hill sphere becomes. This is the reason why every dwarf planet like Pluto can have so many moons. In fact, every celestial object has a Hill sphere, which is why we even see asteroids with moons. And in principle, even moons can have moons. But alas, we have yet to observe such a phenomenon.
Aber sowas hat man leider bisher noch nicht gesehen.
When it comes to the small rocky planets Mercury, Venus, Earth, and Mars, we only find a few moons. The Earth's moon is special because of the unusual way it was formed. It is one of the largest moons in the solar system. The two Martian moons are tiny in comparison. Our moon circles the Earth at a distance of approximately 385,000 kilometers and has a diameter of 3,500 kilometers. It takes about 27 days to complete one orbit. The two Mars moons are much smaller, much closer to their planet, and orbit it much faster too. Phobos has a diameter of just 22 kilometers and is only 9,300 kilometers from Mars. It takes just 8 hours to orbit it once. Deimos is only 12 kilometers across, but it is further out at 23,500 kilometers from Mars, which it orbits in 30 hours. If you were to throw a stone on Deimos, it wouldn't fall back, but enter Mars' orbit and so become a satellite in its own right. Phobos and Deimos, in English fear and panic, the companions of the god of war Mars, were only discovered in 1877. Phobos races across the Martian sky. It rises and sets twice each Martian day, whereby a Martian day is almost the same length as a day on Earth. Where Mars got its moons from is unclear.
According to one hypothesis, they're captured asteroids from the asteroid belt that lies between the orbits of Jupiter and Mars and contains a vast number of small objects. Something was kicked out by Jupiter's gravity and got close enough to Mars to be captured by its gravity. On the other hand, it could be that Mars suffered some large collisions. We can see some massive indentations on its surface, impact basins. Obviously, material must have been ejected, and it's possible that it couldn't escape Mars's gravitational influence, was captured, and that's where the two moons came from.
Perhaps the question will be answered in the second half of this decade. This is when the Japanese mission, Martian Moons Exploration, or MMX for short, will study the Martian moons and bring samples back to Earth. During the mission, a German-French lander is to be set down on Phobos. The fate of the Martian moons is sealed anyway. Phobos is slowly getting closer to its planet and will someday, millions of years from now, crash into it, whereas Deimos is slowly retreating from Mars and could one day, in the even more distant future, escape it. But before this happens, a Martian moon could still have an important role to play for us.
Ein deutscher
At the end of the 1950s, a German aerospace engineer once said, if God had wanted us to explore space, he'd have given us a moon. And he was absolutely right, because our moon is just a 3-day flight away, and thus the perfect proving ground for demonstrating that we've mastered the technologies and can survive independently of the Earth. And if we someday want to fly manned missions to Mars, we don't want to make the risky descent to Mars right away. We need a staging post, which is why Mars' second largest moon, Phobos, is so important to us.
Perhaps one day, humans will travel even deeper into the outer solar system, to the gas giants. The planets Jupiter and Saturn have very different moons on offer than Mars.
Das sind wirklich ganz faszinierende Objekte.
They're absolutely fascinating objects. Many of these moons vent plumes of material that we can analyze. And what we find in them is water vapor and organic molecules. And this naturally makes them objects where we should look for life.
Wirklich Objekte sind, wo wir nach Leben suchen sollten.
Of the 79 known moons of Jupiter, many are just unremarkable little lumps of rock. Quite a number of them circle the planet in a swarm, a long way out. A single orbit takes 2 years, and they orbit retrograde, in the opposite direction to Jupiter's spin. Researchers have recently discovered even more candidates. There could be several hundred. But the focus is on the 4 large so-called Galilean moons. Io, the innermost, is also known as the pizza moon. The vivid colors are due to sulfur. It's the most volcanically active place in the solar system, which is why Io is the only large moon, besides the somewhat smaller moon of Earth, that isn't frozen over. Some volcanic eruptions extend far into space. The tidal forces of Jupiter cause Io's surface to bulge in and out by up to 100 meters.
Io gets heated up so much due to tidal friction with Jupiter that it's actually extremely molten inside and naturally exhibits an extreme amount of volcanic activity as a result. It has 1,500 active volcanoes, which is significantly more than we have here on Earth. They're all active, tremendously active. The eruption columns extend to a height of 300 kilometers. It depends on the size of the volcano, but the largest volcanoes, Pele and Prometheus, they can reach 300 kilometers, and the gas, at least, gets shot out into space. The solid matter doesn't go so high, but falls back and runs down the flanks, the way lava does on Earth.
Volcanism is widespread in the solar system, as we know from Earth. A volcano is like a valve. It serves to even out temperature and pressure differences between hot and cold regions. The interior of planets and large moons is very hot. The heat was originally generated as dust and gas coalesced to form these celestial objects. The decay of radioactive elements and tidal forces cause heating too.
Because space is cold, the surfaces of these planets and moons very quickly solidify, like putting a lid on a pressure cooker. So now it's hot inside and cold outside. The laws of thermodynamics demand that things reach equilibrium. And this can only happen if the hot material inside is transported to the outside. That's volcanism. So it's boiling inside, the lid is on, it gets hotter and hotter, the lid cracks, and then all the magma pours out onto the surface and then irradiates its heat into space.
Ganymede, the third moon, is a giant. With a diameter of 5,262 kilometers, it's the biggest moon in the solar system. It would even qualify as a planet. After all, it's larger than Mercury and is the only moon with its own magnetic field. Like nearly all large moons, Ganymede is an ice moon. Its surface is an icy crust, whereby there are ancient dark areas covered with craters and younger, bright ones with creases that appear very different. It's likely that beneath the crust lies an ocean.
Ganymede is a little bit further away. Jupiter's gravitational force isn't as strong, which means Ganymede's crust is thicker, but it has an ocean as well. The interior won't be quite as hot as it doesn't get squeezed and stretched quite as much, so we have to assume the ocean beneath the ice is at a rather early stage of development. And the crust will be so thick that there's probably no chance of getting at the ocean.
Callisto, the fourth of the Galilean moons, is also an ice moon. It looks dirty and is the most cratered object in the solar system. It too presumably has an ocean of water beneath its 200-kilometer thick ice crust.
Callisto is so far out that Jupiter doesn't treat it as roughly as the others, and it's now pretty much frozen solid. When the ice is dirty, that is, it hasn't melted, it means it's a mixture of ice and dirt. As there's basically no atmosphere, the surface ice sublimes, and the H2O or water molecules disappear, leaving the dust behind. That's why it looks so dark.
And then there's Europa, arguably the most interesting moon in the solar system. It probably has an ocean beneath its ice crust too. All of these moons must have a source of heat. Otherwise, it would be impossible to explain the existence of phenomena such as volcanism and oceans of liquid water at such a great distance from the sun.
So moons can heat up. The question is, where does the heat come from? To find out, we have to take a closer look at a moon. Here's such a moon. A moon is subject to the gravitational pull of a planet, in this case Jupiter. The gravitational force decreases with distance, which means the side of the moon facing the planet is more strongly attracted, and the backside less so. And this difference in pull is called the tidal force. This tidal force causes the moon to deform, and this deformation can have two effects. Either the moon follows an elliptical orbit, and when it's closer to the planet, it gets deformed more strongly, and when further away, less strongly. This leads to a change in the deformation. On top of this is the fact that the moon is spinning too, whereby its orientation to the planet is always the same. And these changes in deformation result in the moon being heavily squeezed and stretched. The closer a moon is to its planet, the more heat is generated, as seen with Io and its volcanism. And when the moon is further away, less heat is generated, but often still sufficient for liquid water to exist, oceans. And it's quite possible that life could arise in such oceans.
Scientists have been searching for extraterrestrial life for a long time, and now the focus is on Europa. This moon is a prime candidate because the ocean, which scientists presume lies beneath its ice crust, is vast. It may contain twice as much water as all the seas here on Earth put together. Its size and gravity are right too, so the conditions are favorable.
When I say life, I don't mean aliens and little green men and the like. We scientists would be happy to find life of any kind, like bacteria. A simple system that can self-replicate and reproduce. We would be literally over the moon just to find that.
Scientists believe that the ice crust covering Europa's ocean isn't all that thick. Who knows what might have developed beneath it?
If there's an ocean beneath this ice crust, which is well protected against the radiation in the Jupiter system and the solar wind, and which is in contact with the rocky core of the moon, the water will dissolve the rock and become enriched with salts. And it will become enriched with nutrients too. Oceans, as we can see from the Earth, are where life has a home field advantage and where it has the greatest likelihood of developing. Which is why Europa is at the top of the list when it comes to places where there could be extraterrestrial life today.
könnte es heute noch Leben geben.
It's possible that the conditions in Europa's ocean resemble those in the deep sea on Earth. Here, extremely hot water full of minerals streams out of the ocean floor from vents called black or white smokers. No place for life, you might think. But it's home to so-called extremophiles, organisms that are adapted to the extreme conditions. Something similar is imaginable on Europa, too.
I think the Earth is always good as an example. And what exists on Earth under extreme conditions may exist elsewhere too. The conditions on Europa could be similar to those we find in the deep ocean and by these black smokers on Earth. Whether or not something has developed there and how, and whether it's similar to what we can find on Earth, or if there's much greater diversity, is something we'll only find out when we can gain access to this ocean.
The study of extreme organisms on Earth is still a relatively recent field of research in biology, with connections to astrobiology.
We're still discovering a great many exotic forms of life on Earth today, so we don't even know our own planet yet. This means that there may, of course, be forms of life in our solar system, and even on extrasolar planets that we can't imagine right now. So we need to do a great deal of research and keep an open mind.
Open to forms of life that are not dependent on the environmental conditions found on Earth, i.e. a certain temperature range and liquid water, oxygen and carbon as the most important ingredients.
Astrobiology also considers other forms of life, and I think that's very important. People have to remain open-minded to things they're completely unfamiliar with. We can't simply check for what we know and say we found it or not. Astrobiology takes a broader view and wonders whether completely different forms of life are possible.
The so-called cryovolcanism on Europa could provide clues as to whether life has developed there. Cryo means cold. We're talking about ice volcanoes. A moon like Europa that gets squeezed and stretched by Jupiter has beneath its ice crust an ocean that is in motion. When the ice crust breaks or cracks somewhere, water and alluvium spray out like the magma in a hot volcano and quickly freeze in the vacuum of space to form ice crystals.
This process is always the same. You have cold space and a hot body, irrespective of what cold and hot is. Space is cold, 200 to 250 degrees Celsius below zero, and the bodies are warm, regardless of whether they're 1,000 degrees or just 10 degrees Celsius. There's always an enormous temperature differential that wants to achieve equilibrium.
The vented water, ice, alluvium, etc., is easier to examine than the ocean itself and may contain evidence of life. NASA wants to investigate more closely. The Europa Clipper mission is planned for the late 2020s or early 30s. The probe is to orbit Jupiter on a highly elliptical trajectory and fly by Europa 45 times in order to assess its so-called habitability, whether the conditions for life are met. The probe won't orbit Europa directly, however.
They're flying to Europa, but they can't inject the probe into orbit around Europa because it wouldn't survive. So now they're planning on making a close approach and then flying way off again, and then flying close again, and doing this a number of times so that they get to observe Europa from all sides. Jupiter is like a massive particle accelerator. You're more or less sitting in the middle of a nuclear reactor when you get nearer, and a spacecraft can't readily withstand that sort of punishment.
The European Space Agency ESA wants to set out even sooner. It christened its mission the Jupiter Icy Moons Explorer, or JUICE for short. A probe will investigate the large Jupiter moons and fly close by Europa a few times.
The details of the JUICE mission haven't yet been finalized, but obviously it must have all the necessary instruments on board to measure things like atmospheric changes, radiation, temperature, and analyze the different regions of the electromagnetic spectrum. So it'll be a very complex mission.
After the flybys of Europa, the probe will then insert into orbit around Ganymede, which is further away from Jupiter and therefore not subjected to such hazardous radiation.
Ganymede is an enormous moon. It's much bigger than our moon. It has a diameter of around 5,300 kilometers, so it's really huge. We think that the conditions there may be conducive to something like life, though not on the surface. The radiation caused by Jupiter is far too strong for that. But it could be that we find something that surprises us.
Another hot contender in the search for extraterrestrial life is Enceladus, a small moon of Saturn, dazzlingly white, that was investigated by the NASA probe Cassini. Not much was known about Enceladus until the scientists studied Cassini's images more closely and discovered something unexpected. They found strange markings on the surface that they nicknamed tiger stripes, and more curious still, plumes of water that shot out into space.
Enceladus has a shell made from ice, but at the South Pole, there are cracks in the ice crust where water is ejected. The water then falls back down to the planet as snow.
Most celestial objects are dark. Enceladus, however, is dazzlingly bright and reflects more than 90% of the incident sunlight. This is because its surface dynamics result in a continual deposit of snow and ice.
Cassini flew by and fairly quickly confirmed that this hypothesis is correct. It's volcanically active. We would regard it as something comparable to the geysers we're familiar with from Iceland. Enormous plumes of water are shot out into space, along with the vast quantities of ice particles. All sorts of stuff flies out too. There's methane and more complex hydrocarbons as well, but it's mainly ice, and this ice rains back down onto the surface.
But not all of the ice falls back on the moon. The remaining particles have a very specific role to play in Saturn's system.
Das Wasser, was zum Beispiel von Enceladus auch abgesondert wird.
The water that gets ejected by Enceladus also feeds Saturn's rings. The material isn't lost. It orbits Saturn and ends up feeding the rings.
Saturn herum und speist beispielsweise auch die Ringe des Saturn.
The particles shoot out at high speed. There must be an ocean beneath the ice crust.
Whether it blankets the interior or there's just a small pocket is unclear. Probably the latter. But it's not big. The energy for this ocean and the volcanism can only come from tidal friction with Saturn. And I mean, it's when I say not big, it's 500 kilometers in diameter. That's like from Berlin to Munich. So it would fit comfortably within Germany.
Although Enceladus is small, many scientists speculate, or hope, that life could have originated in this ocean. Extraterrestrial life.
Ich vermute, dass man als erstes Leben auf Enceladus entdecken wird. Man wird nämlich eine Sonde durch.
We'll send a probe through these water plumes that have formed along the ice fissures and extend kilometers into space. An element analysis may show amino acids, more complex compounds, and even organic material. And then we'll conclude that this moon is home to primitive life. That's my prediction, that it'll be where we first discover extraterrestrial life.
Der Erde Leben finden wird.
Enceladus is one of Saturn's 82 known moons, and not the only one that was investigated more closely by Cassini.
Cassini really was a fantastic mission. Very complicated, but nonetheless successful. Thanks to Cassini, we know now the detailed structure of Saturn's rings and how they formed. In addition, Cassini discovered a lot of new moons and flew by many of them. But the highlight was the ESA probe Huygens. The probe entered Titan's atmosphere and landed on the moon's surface, and it sent back absolutely stunning pictures in the process.
While descending through Titan's atmosphere, Huygens filmed a fascinating world that appears both totally alien and strangely familiar at the same time. Landscapes that are somehow reminiscent of Earth. Titan is the only object in the solar system besides the Earth where liquids persist on the surface. There are even rivers and lakes. The big difference? On Titan, it's a chilly minus 180 degrees Celsius. At these temperatures, the lakes are not comprised of water, but liquid methane. And cryovolcanoes eject not hot lava, but an icy slush.
Titan is interesting because it has a nitrogen atmosphere with methane clouds and methane fog on its surface. The temperatures are inhospitable to surface life, as they are far too cold.
Huygens' descent meant an almost unbearable wait for the scientists involved, because it takes so long for the radio signals from the probe to reach the Earth.
You're sitting on the Earth and have to wait 90 minutes to find out whether it's worked or not. So it's incredibly exciting. And what was sent back was breathtaking, at least for me. The first images were of it flying into a somewhat larger valley. You can see a coastline. You can see rivers that flow into this valley plain. It looked like you were flying with a plane along the North Sea coastline on a rainy day, because the atmosphere is extremely dense. It really was incredibly exciting.
The Cassini-Huygens mission was a textbook example of successful international cooperation in space. Cassini was a NASA probe that carried the European Huygens lander to Saturn on its back. Once there, Cassini then acted as the lander's radio relay station. NASA plans to return to Titan in a few years. This time, they want to send a quadcopter, that is, a robotic rotorcraft. The mission's name? Dragonfly. This Dragonfly will spend 2 years flying around exploring the various regions of the moon. It should also ascertain whether precursors of life are present in the frigid methane lakes.
Imagine you went on a mission to Earth and landed in the Sahara. You wouldn't get a representative picture of the planet as a whole then, so you have to be able to travel around large areas. And you could do that with a drone, and a drone could fly on Titan too, because Titan is the only moon with an atmosphere. In order to fly, you always need an atmosphere in order to generate lift, like propeller aircraft can fly here on Earth.
Another of Saturn's moons was puzzling scientists because it seemed to regularly disappear and then appear again. Its name? Iapetus. Thanks to Cassini, we now know that the front side of the moon is as black as soot and the back as bright as ice. When the dark side is facing Earth, the moon becomes practically invisible. Why the two halves are so different remains a mystery. In addition, the moon has a mountain ridge on its equator that makes it resemble a walnut. How this mountain ridge formed is not yet known either. A neighbor of Iapetus is the moon Mimas. Nothing special really, but it has many fans because it resembles the Death Star from Star Wars. And then there are the so-called shepherd moons of Saturn, small moons that keep Saturn's rings in shape. These moons herd the ring particles, like shepherds herd their sheep. Planets like Jupiter and Saturn generate tides on their moons, thereby producing heat. These tides have yet another effect, though, as we see from our moon.
Tidal forces have a very interesting long-term consequence because the internal friction causes the speed of rotation to decrease. This means that the moon spins ever slower. How long does this go on for? Well, it goes on until the rotational period of the moon matches its orbital period around the planet. At this point, the same side of the moon always faces the planet. This is called a tidal orbit. And because the moon's rotation is synchronized with its orientation, it doesn't get stretched and squeezed anymore. Heat is no longer generated, and the moon cools down. This has happened to our moon. Incidentally, tidal orbits like this occur throughout our solar system, including the case of the Martian moons Phobos and Deimos.
The effects of these tidal forces is even more obvious with Pluto, the dwarf planet at the edge of the solar system. Pluto has a moon named Charon, whose diameter is half that of Pluto. The tidal effect is so great that both bodies are tidally locked with one another. The same side of the moon Charon always faces Pluto, and the same side of Pluto always faces its moon.
They each spin once about their respective axes for each complete orbit about their mutual barycenter. So they're both tidally locked to each other. Pluto and Charon always present the same face to one another.
The NASA probe New Horizons flew close by the odd couple in the summer of 2015. Instead of the expected dead rocks, it found two fascinating multicolored worlds dancing around one another. Triton is also a strange moon. It orbits its planet, Neptune, backwards. Triton is another large ice moon, presumably with an ocean beneath its ice crust. Its orbit is retrograde, which means it orbits in the opposite direction to its planet's spin. The question is, how did it come to be in this orbit?
When a system like this forms, Jupiter, Saturn, Uranus, Neptune, it's from an accretion disk that rotates. And when moons form in it, they naturally rotate in the same direction as this accretion disk, or in this case, the planet rotates. When its orbit is retrograde, it's not as straightforward. Retrograde anomalies can happen when a moon is captured. This means a foreign body traveling on a different trajectory approached Neptune too closely, got slowed down, and forced into its orbit.
The surface of Triton is an icy minus 235 degrees Celsius. No other moon in the solar system is colder. NASA scientists would like to investigate Triton with the probe too. Up to now, we only have the images taken by Voyager 2 as it passed by in the summer of 1989. The new project, named Trident, has to compete with other projects for the available funding, however. Humans have zero chance of survival on planets like Jupiter or Neptune. Their gravity and pressure are much too high. The situation is different on the numerous moons of these planets, however. Is it conceivable that we could settle there in the future? Or are these just science fiction fantasy?
Do colonies on moons make sense? Yes. But the moons would have to be at least as large as Earth's moon. Take Phobos, the largest of the Martian moons. It's so tiny that its gravity is just 1,000th that of Earth. A small jump and you'd float off into space. Moons as raw material stockpiles? Well, I don't know of any moon that consists solely of gold and diamonds. And we have enough of all the other raw materials on Earth. They could be a good launch pad for space stations. And one final thought. Could there be exomoons somewhere out there? That is, moons orbiting exoplanets. We know today that this must be the case. There have to be a lot of moons out there. But because they're so small, smaller than the exoplanets, they're extremely difficult to detect. But let's wait and see. Maybe we'll manage to in the future.
Some moons are just lumps of rock, barren and empty. Others are absolutely fascinating. Io has more volcanoes than any other object in the solar system. Titan amazes with icy river and lake landscapes. Europa, Enceladus, and Triton have oceans hidden beneath their thick ice crusts. Could exotic life forms swim in these oceans, perhaps? The moons of our solar system, the silent companions of the planets, are unique worlds in their own right, full of mysteries just waiting to be investigated. The probes we send out are getting increasingly sophisticated each time. And who knows, maybe humans will fly there one day themselves. Not to mention all the exoplanets out there in the Milky Way, a great many of which probably also have exomoons, with mysteries of their own. Our Earth orbit is filling up at an alarming rate. Nearly 6,000 satellites are now circling our planet. About half of them are dead and circle the Earth as space junk. Millions of pieces of debris are also hurtling alongside them in orbit. And the trend is increasing. Space junk can have devastating consequences. It threatens not only manned space travel, but also our satellite-dependent digital world.
Space junk is and always has been a major topic. But let's be honest, nobody really knows exactly what's going on. How dangerous is space junk, actually? Under the current conditions, can we even continue to travel into space? Are our astronauts safe at all up there in the space station? One example, a particle measuring just 1 millimeter in diameter recently smashed into the pane of a module of the space station and damaged it. And I can assure you that had it been 1 centimeter in diameter, it would have caused a catastrophe.
The International Space Station circles the Earth at an altitude of about 400 kilometers. Its speed, 28,000 kilometers per hour. The orbit of the ISS is continuously monitored from the Earth, partly to avoid a collision with debris. But the object that damaged the pane of the observation cupola in 2016 was much too small to have been detected. Perhaps the fragment was just a splinter of metal or a particle of paint. A 1 centimeter particle, on the other hand, could have been life-threatening for the crew, or at least caused serious damage to the space station.
Space junk in Earth orbit is dangerous for people on the International Space Station simply because it's moving at very high speed, 10 kilometers per second. So here's the thing. When something is moving at very high speed, even if it's very lightweight, its so-called kinetic energy is very high. The kinetic energy then becomes as high as the energy of multiple kilograms or even tons of explosives, and so you can understand how extremely dangerous it is just to collide with some little screw flying around out there.
In June 2011, an unidentified fragment crosses the path of the ISS. The object is detected too late to execute an evasive maneuver. The space station is evacuated. For safety, the crew boards the 2 Soyuz capsules. The object passes the space station at a distance of just 250 meters.
Normally, we try to detect the approach of such space junk well in advance. Sometimes, however, objects appear suddenly because they remain unseen for much too long. Examples of such objects include ones with very eccentric orbits, which cannot be measured very often, where the opportunity to measure them is very limited.
About twice a year, the ISS executes evasive maneuvers to avoid large debris or dead satellites. An evacuation into the Soyuz capsules is a genuine emergency. And even then, the crew members need enough time. The space station is at continuous risk of being hit, even though the debris in such low Earth orbits does not stay in space forever.
Service life in Earth orbit primarily depends not on the size of the object, but rather on its altitude. When I'm in the low range and low Earth orbit, then I still have a residual amount of Earth's atmosphere there that has a braking effect on my objects. In other words, atmospheric drag causes them to lose orbital energy and fall back to Earth as a result. So, as an order of magnitude, we say that an object placed at the altitude of the International Space Station, about 400 kilometers, will remain in orbit for 1 year. After that, it has left orbit. At 600, 650 kilometers, there you have to expect a service life of about 25 years.
The available space around our planet is gradually becoming scarce. It is estimated that there are 35,000 objects in Earth orbit, which are larger than 10 centimeters and no longer have a function. They represent the most dangerous segment of space junk. Observers on Earth know the orbital data concerning about 20,000 of those objects, but the further they are from the Earth, the harder they are to locate. These objects are monitored primarily by the U.S. Space Surveillance System, a network of telescopes and radar systems which continuously monitors Earth orbit. It is under the control of the U.S. Department of Defense. Established already in the early 1960s, that surveillance system is now part of the newly created United States Space Force, the space arm of the U.S. Armed Forces.
In the past, the Americans always provided the data to us very reliably. We are currently in the process of developing the relevant competences in Europe too. It's an SST program, or in other words, a tracking program. It's being financed chiefly by the European Union, and the ESA is also involved, of course, to also provide access to all the information collected. I think all this data should be made public. It's not secret data. We say it, but then we don't say where it's flying. Well, you can see that for yourself.
Of course, the governments of all countries want to know what objects are flying out there in space. That healthy curiosity originated during the Cold War. Intercontinental missiles travel a large share of their trajectory in space.
They were detected with radar systems, systems that were originally designed to detect intercontinental missiles. From those systems, the first orbital data catalogs were then developed. And then for very high objects for geostationary Earth orbit, those objects out there were just detecting using telescopes. And it's actually true that there are certain objects whose orbital data are not published. But it's also only fair to say that most of those objects are in very low orbits. That means when they fall out of orbit, they disappear. And some of those objects also disappear from Earth orbit very quickly. That means we have to assume that those objects undergo controlled re-entry, for example.
Orbital data from Earth orbit are primarily recorded and published by the U.S. military, except for its own secret objects. But even the U.S. military is still unable to monitor dangerous, centimeter-sized debris.
In space, close to Earth, all particles have the same speed, roughly between 7 and 8 kilometers per second. That corresponds to 25,000 to 28,000 kilometers per hour. The question is, how much force does that represent on impact? I've brought along an example of such an impact site for you here. This is what it looks like. A 1-centimeter ball has been fired into a massive block of aluminum right here. It's pretty heavy. Now, the question is, how can the International Space Station protect itself from something like that? An aluminum block like this is of no use at all. And the answer is, you have to use a trick, the so-called Whipple shield. The Whipple shield provides just enough protection against such impacts. For larger or faster particles, however, even the Whipple shield won't help.
The astronomer Fred Whipple invented the shield, which is designed to protect manned and unmanned spacecraft against debris and micrometeors. All endangered areas of the space station are fitted with such shields. A Whipple shield normally comprises 3 layers, whereby the first layer is used to break up and disperse the penetrating object. This distributes the energy among many fragments, which are then absorbed by the remaining layers. The question is not whether the space station will be hit, but rather where and how large the object is.
There's a gap in our knowledge of objects, ones we cannot see and whose orbit we cannot track. There are developments aimed at also monitoring such small objects, but there are huge technical hurdles to overcome. For one thing, we have to be able to detect these small objects in the first place. That means a system must be powerful enough to detect a small object in order to track its orbit. And I am receiving more and more measurements. At the moment, I have roughly 20,000 objects in the catalog. When I go into the centimeter population, then I suddenly have 100,000 objects whose orbits I have to measure.
And then, when the fragments in the millimeter range are added, the number of debris particles rapidly grows to many millions. In February 2009, two satellites collided in orbit for the very first time. The defunct Russian Cosmos 2251 struck an Iridium communications satellite, a worst-case accident.
At first, the resulting debris continues flying more or less along the same orbit because it has such a high orbital velocity. The additional speed then imparted by such fragmentation causes the cloud of debris to expand over the course of time. This means that within a relatively short period of time, the cloud of debris is no longer compact. When I look again weeks or months later, then the orbits have begun to move apart from one another. That's called orbital drift, which means that the orbits that were once at the same orbital level continue drifting apart until after a few months or years, this debris is ultimately distributed throughout Earth's orbit in that orbital region and at that altitude.
More than 3,000 detectable objects have been set free by the collision and are now careening around the globe. A tremendous danger for other satellites.
The available space that Earth orbit provides is actually smaller than it appears to be because only certain orbits are of particular interest. This is the so-called geostationary orbit, 36,000 kilometers above the surface of the Earth. When you place a satellite there, then it remains at that fixed point. The Earth then rotates exactly together with the satellite, and so you have a satellite that always stays over the same point. And it's particularly easy for you to communicate with that satellite. So that orbit is in especially high demand and should not be cluttered up with debris. And then there are the orbits in which the International Space Station is located several hundred kilometers above the Earth. They're also of special interest because there's not really all that much room up there, considering the fact that every small screw represents a serious risk. So it seems like there's plenty of room, but in reality, there's not so much.
Orbits around the Earth are getting crowded. The near-miss collision of the U.S. space telescope Fermi and the defunct Soviet spy satellite Cosmos 1805 is further proof. Only by changing its orbit did Fermi manage to escape destruction by a Cold War relic. The old Soviet reconnaissance satellite missed the telescope by barely 9 kilometers. The rescue maneuver used the rocket thrusters that will also propel the telescope into the atmosphere to burn up at the end of its service life.
We also have several thousand out-of-service satellites flying around the Earth. And that's, of course, an issue when we consider space as infrastructure. And infrastructure all cluttered up with rubbish is not a good one.
Without communication satellites, Earth observation and weather satellites, or navigation satellites, the digitized world as we know it today would no longer work. We have become completely dependent on data streams from space, even if we're not always aware of it in everyday life. Nowadays, satellites enable telephone conversations, television, and the internet. So every time you use your smartphone also involves aerospace applications. Today, the orbits around the Earth are an important and sensitive economic factor, one that every country tries to safeguard for itself. The new German space radar Gestra, for example, will also provide for greater security in space.
A national system enables a country's own independent assessment capability. That means that we can use it independently from other nations to determine what's out there in space and whether danger threatens our satellites.
This state-of-the-art radar system comprises 256 separately controlled transmitters and receivers and can monitor objects in low Earth orbit around the clock. In that way, Gestra provides continuously up-to-date situational awareness in space. But the acquired data are also added to the European Orbital Data Catalog.
The system is designed to monitor low Earth orbit. That means we can detect objects orbited at an altitude of between 300 kilometers and 3,000 kilometers. And the system itself is a so-called phased array radar. Phased array means that the direction in which we look need not be determined by the mechanical rotation of an antenna, but rather can be set up purely electronically. This enables us to search a large area in space in a very, very short period of time, laying out a search grid with which we can then detect objects that fly through that search grid, and then we can track their orbit.
The radar is operated from the Space Situational Awareness Center of the German Armed Forces. And the system will also make it possible to achieve gradual independence from the U.S.-American Orbital Data Catalog. Every rocket launch leaves space junk in orbit, and the limited service life of satellites only makes matters worse. Depending on the altitude of their orbit, those defunct satellites then continue to drift in space for a very long time. The extreme conditions that prevail there cause materials to fatigue very rapidly. And as a result, many objects break up on their own into smaller fragments, which are in turn distributed around the globe where they endanger manned and unmanned spacecraft.
So, how was it back then with the space shuttle? Well, first of all, the space shuttle was much smaller than the space station, and missions only lasted 1 or 2 weeks. And that's why, according to NASA, only 1 out of 1,000 missions were at risk. And that, in turn, was the reason why the shuttle had no protection. NASA told us astronauts that if an object hits the shuttle, you'll just have to put on a pressure suit and return to Earth immediately. Of course, the shuttle did suffer impacts from time to time, but they were only very small particles and therefore caused only relatively minor damage.
The space shuttle was designed to be NASA's workhorse. The 2 space shuttles that Americans lost cost the lives of 14 astronauts. Though neither of those accidents was caused by space junk, the space shuttles were not invulnerable to debris hurtling through space. There were numerous near-miss collisions with objects in space, like this piece of junk that flew past the tail of the Atlantis on mission STS-43. Nor were small impacts rare. Hits like these in the flight deck panes of the space shuttle could have been fatal had the debris been a little larger. Extensive damage was documented during every routine inspection upon return from space, especially after the missions involving the Hubble Space Telescope, which circles the Earth at an altitude of about 550 kilometers. Numerous impacts were identified. The Hubble telescope was transported into space in the cargo bay of the Space Shuttle Discovery and placed in orbit. 5 more shuttle flights then returned to the telescope on repair and maintenance missions. And technicians regularly found a large number of impacts in the space shuttles upon return to Earth. And then, during a service mission in 2002, one of the solar modules of the Space Telescope was also replaced. The old collector was brought back to Earth, and the scientists found several thousand craters on it caused by space junk, some of which measured several millimeters. Testimony to the serious risk of fast-flying particles orbiting at that altitude.
At 28,000 kilometers per hour, even small fragments can cause damage, of course. The film Gravity provided us with a very impressive depiction of that. This is a genuine risk that can endanger astronauts. It can also endanger the International Space Station. And with that in mind, we must do something to protect against both large and small objects. The issue must be taken seriously, very seriously.
Sonic boom's announcing Discovery's arrival. It's now just 68 miles away from Kennedy Space Center. 27,000 feet.
The double sonic boom announces the return of Discovery after a mission in Earth orbit. NASA's space shuttles completed a total of 135 space flights, and ultimately, it was pure luck that no third accident occurred, caused by a large enough piece of space junk crossing the path of the space shuttle. The internet site stuffin.space offers an amazing view of the Earth. Based on the U.S. Orbital Data Catalog, the American programmer James Yoder creates a three-dimensional map showing all the objects in Earth orbit in real time.
Now let's see just what the space junk situation actually looks like. To do so, I have an app here that displays an animated graphic of scrap for me. Debris from an American catalog of space junk. What do we see? We see different colored points. Red indicates active satellites. Blue means broken ones. And these gray points are other debris. First of all, we see that most of the pieces are flying close to the Earth. That's the so-called near-Earth space. Now, when I zoom out a little bit, then we get a better overview and we see that out here we have a string of pearls. Those are the geostationary satellites, and that means the active ones, all in red. But we also see that there's a sort of ring around the geostationary orbit, and that's all the ones that can no longer be controlled properly. So they leave this string of pearls. In addition, we see here a sort of cloud of satellites, which are somewhere in between. Those are the navigation satellites of the Chinese and the Americans, but also the Europeans. And now, what we'll do is, we'll pick out any object at random. So I tap here on one of these points, this one, for example, and we see a Cosmos satellite, a Russian satellite, launched in 2016. You can see that here. And here in green, you see its orbit. By the way, this red string of pearls that you see here, those are the brand new Starlink satellites from Elon Musk. He recently sent them into space, and now they're circling the Earth like a string of pearls.
Starlink is a network of small satellites that Elon Musk's aerospace company SpaceX uses to provide high-speed internet from Earth orbit.
Starlink
is Elon Musk's project to build a constellation. His is now the operation with the most proprietary satellites out there. It's really quite amazing. He has accomplished so much here. But Starlink did have two aspects that have to be taken into consideration. The first is that it's a constellation that places many, many satellites out in space, thereby also clearly raising the question of space junk. And the second is that Starlink obviously made them easy to see, and astronomers were not very thrilled about that.
Scientists are worried about their unobstructed view of space. Today's time-lapse recordings of the starry sky are already interrupted time and again by satellite clusters. And the Starlink constellations are clearly visible in the night sky, especially in the deployment phase. The Internet from space will be accessible around the globe, and it will require a huge number of mini-satellites. SpaceX has applied for launch approvals for up to 30,000 Starlink satellites in the next few years. New space. Clearly, the ever-increasing commercialization of space still has some surprises in store for us. The once ridiculed SpaceX idea of landing the first stage of a Falcon rocket autonomously for reuse has already become routine. This does not prevent space junk, however, because the upper stage of Elon Musk's rocket remains in space. It takes multi-stage rockets to reach Earth orbit, and the upper stages that remain in orbit are what actually cause the big problem.
The real question is, how do we measure the risk? How much debris can be created when an object is struck and disintegrates? And the upper stages are particularly significant here due to their large size and weight. Because when a large, heavy object is struck, of course, the impact produces a much higher number of fragments than when a small satellite is hit. So it might be an overstatement to say that there are very, very many upper stages, but the risk inherent in an upper stage like this, when struck by an object, that risk is clearly higher than with a small satellite.
Since the very first rockets were launched into Earth orbit, people have also been leaving their rubbish there. Starting from the 1960s, aerospace activity experiences a boom. In the space race between the two superpowers, the USSR and the USA, an ever-increasing number of ever more powerful rockets are fired into space. And in so doing, they also leave more and more objects in orbit. At the dawn of the aerospace age, however, this is of no concern to anyone yet. The Apollo moon missions alone send several tons of scrap into space. Much of the debris left behind then is still circling our Earth today.
We still find objects from the early phase of space travel in orbit. The Vanguard 1 upper stage and satellite, which were launched in 1958, are still in Earth orbit. That's essentially the oldest space junk to be found.
The remnants of a particularly adventurous plan also originated from that time. The U.S. military wanted to use hundreds of millions of copper needles to create an artificial ionosphere around the Earth. The project, known as West Ford, failed. The clusters of copper needles, however, continued to clutter the orbit to this day. In 2007, China raised tensions by destroying one of its own weather satellites. The Russians and the Americans also tested such anti-satellite missile systems, but their targets were in lower orbits. Within a few months, the debris burned up in the atmosphere. The defunct Chinese satellite Fengyun 1C, however, was orbiting at an altitude of 850 kilometers. As a result, China's space weapon test scattered an estimated 40,000 fragments in orbit for a long time.
I don't understand why China decided to shoot down a satellite in such a high orbit. They must have known that the debris will remain in orbit for many, many years. In some sense, of course, the project was a show of force. They wanted to show other nations that they were capable of doing this. Unfortunately, however, it has had rather negative consequences for both military and civilian aerospace.
Then in the spring of 2019, India tested a satellite killer. The decommissioned Indian military satellite that they shot down was flying at an altitude of barely 300 kilometers. So most of the debris from the explosion burned up in the atmosphere relatively soon.
In recent decades, we've noticed that a few countries around the world apparently thought they also had to demonstrate their power in space by claiming they can play war even up there. I explicitly refer to it here as playing war and not waging war. I condemn it, of course. I have absolutely nothing good to say about it. For one thing, we already have enough problems here on Earth. Surely we don't need to fight one another in space as well. Moreover, they generate space debris, and we have enough of that. We should take the necessary steps to clean it up instead. The ESA does not participate in any of these military projects. The ESA Convention expressly states exclusively for peaceful purposes. And that's why we don't participate in such activities. And I also wish they would just cease.
After the USA, Russia, and China, India is now the fourth nation that can use rockets from the Earth to shoot down objects in space. Right from the beginning, with the advent of satellites, armed forces sought ways to destroy enemy objects in orbit. The U.S. Air Force, for example, also tested, among other things, anti-satellite missiles fired from aircraft, with success. But then the research program was canceled at the end of the 1980s. The USA has since focused on ship-based anti-satellite missile systems. But Russia has now resumed air-launched missile tests using MiG-31 combat jets that carry anti-satellite weapons up to the edge of the stratosphere.
Knowingly producing space debris simply by attempting to shoot down a satellite for military purposes, that's a little like polluting the environment. It can be tolerated up to a certain point, but eventually everyone suffers from it. And the same goes for space debris. Once you reach the point where you can no longer operate satellites, then of course you've gone too far.
Collateral damage from military anti-satellite weapons testing is a major annoyance, especially when a target is destroyed at a high altitude. The Chinese show of force created debris that will continue to orbit the Earth at high speed for almost 1,000 years.
Although we have plenty of debris out in space these days, we shouldn't forget that space is also pretty darn big. It can hold a whole lot of stuff. And that's the reason why the distance to a dangerous piece of space junk is currently about 400 kilometers. For the moment, the probability of a collision is still relatively low. But here's the long-term problem that we're going to have. Every tiny piece of debris can collide with another piece of debris, and that will create tens of thousands of new pieces of debris. And every piece of debris is just as dangerous on impact.
A collision of two objects can trigger something like a chain reaction, which theoretically accelerates and can no longer be stopped.
There's a risk that in certain Earth orbit regions, the quantity of debris eventually grows so high that you can't really conduct aerospace operations with reasonable means anymore, because you have to make too many evasive maneuvers just to keep your satellites safe. And that can really happen. It's called the Kessler syndrome. This could happen when space debris starts to collide with other space debris, creating new debris again and again with each subsequent collision. This then leads to a sort of chain reaction, where debris creates more debris through a continuous series of collisions.
This horror scenario was developed and mathematically modeled by the astronomer Donald J. Kessler. Sustained by this cascade effect, the unstoppable reproduction of debris could rapidly destroy all active near-Earth satellites. The conveniences of our digitalized world would come to an abrupt end.
Up to just a few years ago, there were far fewer active satellites. What we see today represents a significant change in the way the aerospace industry operates. There are many more small satellites today. Satellites you can purchase almost off the shelf, or whose components are commercially available and can be used to assemble satellites, almost like with a modular kit. That would only be a slight exaggeration. And that's why the number of active satellites in Earth's orbit is so much higher today than it was maybe 10 years ago.
The best way to reduce space debris is to bring the worn-out satellites back to Earth. And that's what they do anyway, sooner or later. It's only a matter of time. An object orbiting at an altitude of 160 kilometers falls back to Earth again within 24 hours. For satellites in a 36,000-kilometer high geostationary orbit, however, it takes longer, several million years. But they all come back eventually, without exception. There are re-entries every day as a result, and most objects burn up completely in the process. But some pieces of debris survive the ride through the atmosphere. Tanks made of stainless steel or titanium are the most common examples. The largest known piece of debris in space is the defunct environmental satellite Envisat.
Envisat is a relatively large satellite, a very complex instrument, a very complex satellite, about as large as a minibus. Yeah, roughly the size of a VW bus, in that range. Because it's so large, if Envisat were to be hit by debris, the impact would produce a very, very large quantity of debris. So that means the risk potential in the event of an impact is higher than with a small satellite.
The defunct ESA satellite orbits the Earth at an altitude of a little over 760 kilometers. Since 2012, scientists have lost all control over this 8-ton boulder. Because Envisat is traveling in an orbital region with a particularly high object density, it constitutes a serious danger.
Envisat
is a real problem because it will take a really long time for it to come back down. But nature is helping us out here because residual air up there creates drag that causes the satellite to come back down very, very slowly. Although it will take Envisat 150 years, it will indeed come down eventually. All other satellites come down faster and then even burn up in the atmosphere. Not completely, unfortunately. In some cases, scraps remain that then fall to Earth. Do they represent a danger to us humans? No. If every human on the planet stood close together, we would just barely cover an area the size of Lake Constance. And it's certainly highly unlikely that a piece of debris would just happen to fall into Lake Constance. Nevertheless, that means we have to bring as many defunct satellites back down as possible. And one perfect example was the Mir space station. It was still controllable, and the Russians managed to make it fall into the Pacific Ocean.
The Russian space station Mir is the largest man-made structure ever removed from space. Launched in 1986, Mir reached the end of its service life in 2001. Mir was one of the greatest successes of the Soviet aerospace program. And prior to the establishment of the International Space Station, it was humanity's only continuously manned outpost in space. After the station was abandoned, the Russians could not simply leave the 124-ton uncontrolled structure in orbit.
The Mir space station occupied a very low Earth orbit at an altitude of about 400 kilometers. Such objects are also then brought back down to Earth. But that means we want their entry to be controlled, of course. So we reduce the object's orbital altitude, either by natural means or with rocket thrusters, till it reaches a sufficiently low Earth orbit. And then we fire rocket thrusters to actually cause the object to crash. And that means a controlled fall in a controlled corridor. With the Mir station, for example, this was carried out by a docked progress module, which then ultimately made the final burn, as they say, that brought the Mir station into a controlled re-entry.
With an object the size of Mir, uncontrolled re-entry would have been too great a risk. Under the direction of the Russian Space Agency, the complex recovery mission starts on March 23, 2001. With several precisely targeted thrust maneuvers of a docked Progress spacecraft, the station is pushed into a lower orbit and then deliberately forced to crash. Mir enters the Earth's atmosphere over the Pacific Ocean. The station breaks up. Its separate pieces burn up in the sky. Falling remnants of Mir are scattered across 1,500 kilometers of ocean, far from civilization. The mission is a success. A controlled crash is also the fate in store for the International Space Station. The final decision on its decommissioning has yet to be made, but in the end, most of the ISS will also burn up, and the rest will fall into the Pacific.
No doubt it's so large that some of it will beat the odds and make it all the way down. The whole thing won't burn up. It's the heaviest components that probably won't have that satisfaction. But the International Space Station has no radioactivity-based energy sources. So you might say there are no dangerous batteries on board. In that sense, what comes down then won't actually pose any danger anymore.
It remains to be determined whether a Russian or an American spacecraft will give the mortal blow that sends the International Space Station falling toward Earth. But its deorbiting scenarios are already under development.
To hit an intended crash site with pinpoint precision, that's really a high art that only very few people ever master. And that's why many satellite operators use another method. Simply bring it down and pray. Well, that works too. Meanwhile, there are more and more satellites in space, large and small. The small ones are not a big problem because most of them burn up. Only the large ones might become a problem. But the operators promise that in the future, they will systematically pull their satellites back down at the end of their service life. The question remains, can anyone put a satellite in space? The answer is yes, as long as that citizen's government says yes, because that government ultimately bears the liability for it.
The space surrounding the Earth has become a huge economic zone. The data from space are highly coveted and promise good profits. Highly complex technology can now be housed in tiny packages. Using that approach, more and more mini-satellite designs are being developed for specialized applications. The prices of these tiny satellites make going into space attractive, even for private companies.
We see that companies like Elon Musk's and also Amazon, among others, are thinking about constellations in order to have full coverage of the Earth. For example, for telecommunications or for Earth observation or navigation. These are very interesting approaches. But just now, when we're thinking about sending hundreds or thousands or tens of thousands of additional satellites into space, that's really when the issue of space debris becomes more important than ever, even more exciting and even more crucial, to develop technologies that also ensure the purposeful avoidance of space junk now, and not to just wait around happy as pie for the next 10,000 satellites.
There are strict rules in the satellite business, but not everyone follows them. When its application for approval to launch 4 test satellites was rejected, the U.S.-American startup Swarm Technologies just went ahead and launched them into space from India anyway. The FCC, the U.S. regulatory agency with authority over broadcasting, satellites, and cable, was not amused and slapped a $900,000 fine on the young entrepreneurs. Swarm Technologies has since obtained all necessary approvals and promises low-cost data exchange between devices on the ground via its SpaceB satellite network. Data from space also open up brand new opportunities in land management. Information applicable to soil analysis or irrigation, for example, or for the networking and control of agricultural machinery.
The downside of having many small satellites is that maybe one gets left behind or one of the little guys breaks down and then I produce space junk again. The trend is perfectly understandable, but so is the trend that in the end we also think about the waste and then dispose of it properly.
The future indeed belongs to constellations of small satellites. Space is open for private entrepreneurs. And more providers are supplying data from space for a continuous stream of new applications.
It's crucial that such constellations implement very highly reliable space debris prevention systems. Once they can guarantee that, then such constellations can also be operated safely in Earth orbit.
Networks of small and mini satellites fill important data gaps, and this is especially true in the field of climate and weather observation. They can be put to very specific uses and are nevertheless relatively inexpensive, rapidly equipped, and easy to operate. And because they orbit very close to the Earth, they're exposed to less cosmic radiation. Satellite clusters provide exhaustive data collection, and meteorologists are particularly reliant on continuous and verified measurements.
What can we do about this space junk problem? It's actually quite simple. We have to clear away these old, dead satellites, because when they're hit by a piece of debris, they fling apart into more debris. That's why the Americans have established an Orbital Debris Program Office. But it's just a paper tiger. It has no substance. The ESA is actually better. It has planned a concrete mission, the so-called Clear Space One. And with it, they want to bring an old rocket part of a Vega rocket back down from orbit.
With Clear Space One, a private company has been contracted for the first time to recover a piece of debris from space. The first active cleanup mission in space. It is a test that will remove from space an adapter piece weighing about 110 kilograms. And the mission is also conducting research on a possible future market. Satellite operators could be obliged to bring back their satellites themselves, or have a contracting company recover them for a fee.
Space agencies have discussed the topic of space junk among themselves time and again for many, many years now. Most of them say, we're monitoring, we're monitoring, we're monitoring. But monitoring still isn't disposal. And that's why, at the meeting with the ministers in 2019, I proposed to launch an actual mission now to genuinely reduce space debris.
There is no doubt that the ever-increasing number of satellites launched into space will cause serious problems in the future. And the most reasonable approach to solving that problem is to bring defunct satellites back to Earth.
If we could find a way to bring this space junk closer to the Earth, into the outer atmosphere, then the outer atmosphere, the drag, would slow it down anyway, and then sooner or later it would enter the atmosphere and burn up. That would be the most elegant solution.
Small rocket thruster modules could lower the orbit of defunct satellites. In lower orbits, a sail would also increase drag enough to cause the satellite to fall back to Earth faster. Or the space debris can be captured with a net and towed towards Earth. But the best option would be to equip all satellites with system-specific return mechanisms.
The approach is actually to try to achieve more sustainable aerospace operations. Basically, it's no different than for us here on Earth. When I avoid creating waste in the first place, or when I can use my systems longer, that's better than throwing things away and then having to clean up afterwards.
One successful example of extending the useful life of a satellite is the so-called MEV, the Mission Extension Vehicle. This probe is used to reactivate satellites that have run out of fuel but are otherwise still functional. In February 2020, this mini spacecraft successfully docked with the Intelsat 901 communications satellite and extended its life by 5 years.
What do we have to do to get this space junk problem under control? Well, we have to clear away all these dead satellites. This is technically feasible, but awfully expensive, because there are so many of them. And that's precisely why all space nations are holding back. But there's cause for hope, the Clear Space One mission of the ESA. What do we do with the many small pieces of debris? Well, there's nothing we can do about them. We can only wait until they come back down. And if we do nothing at all, we'll have a huge problem. Then the Kessler effect will overwhelm us. Then we'll have so much debris that we'll no longer be able to operate aerospace programs at all. Nobody wants that. So we have to act.
Satellites allow people the world over to communicate, transmit television signals, and maintain our networks worldwide. Earth orbit has long since developed into an economic market, and the available room around the Earth is gradually becoming scarce. More and more satellites in space are leaving more and more rubbish behind. Space junk. Year after year, this raises the risk of collisions involving satellites and their remnants. We are putting our aerospace programs themselves in danger, and along with it, our modern life in the digitalized world. Humankind is entering a new era of space travel. Astronauts are set to return to the moon before the decade is out, and scientists and visionaries say humans will soon set foot on a foreign planet for the first time, Mars.
We already visited the moon back in the 1960s and 70s. Nowadays, everyone is talking about flying to Mars. Why is this? Well, it's actually quite simple. Mars has a solid surface. This means we can walk around on it. And even more importantly, the temperatures there are reasonably tolerable for human beings. And that's precisely the reason why life could potentially have evolved on Mars many billions of years ago. We just need to fly there and have a look. And we're familiar with the technologies we'd need to do so. This means that Mars is a feasible distance away.
July 30th, 2020. An Atlas V launch vehicle lifts off from the Kennedy Space Center in Florida. An hour later, the spacecraft separates from the upper stage of the rocket and sets course for Mars. On board, the rover Perseverance. It's NASA's most ambitious mission to the red planet yet.
Mars is very interesting because it's a relatively large planet. In the past, the conditions on Mars in terms of atmosphere, temperature, and so on were quite similar to those on Earth. But we don't see any Martians wandering around there today. So was there once life there or not?
NASA has already sent around 40 successful missions to Mars, including 4 rovers. These spectacular images were transmitted to the Earth by Curiosity. But up until now, all of the probes and Mars rovers have only encountered a cold, lifeless desert world. The planet's atmosphere is thin. Its density is just 1% that of Earth. And it consists of 95% CO2. Cosmic radiation, 30,000 times stronger than on Earth, bombards the surface, and it's cold.
You have to imagine Mars as being like a polar desert. It's incredibly cold and incredibly dry. There's no air to breathe. The average temperature is around -60 degrees Celsius, and it drops as low as -133 degrees Celsius. But it can climb to around +20 degrees at the equator in summer. But it's very inhospitable on Mars.
None of the Mars missions thus far have found any evidence of life. This is now the job of Perseverance. The 6-wheeled robotic vehicle is about the size of a compact car and has extremely sensitive instruments on board. These include 19 cameras, ground-penetrating radar, various analytical instruments, X-ray detectors, and 2 microphones. With all that, the rover should be able to detect the traces of ancient life forms, assuming they once existed.
It's actually quite possible, because at the exact same time that life was emerging on Earth, namely 3.7 billion years ago, habitable conditions prevailed on Mars. We've conducted a lot of tests in the lab, and they indicate that microorganisms could have actually been able to form and survive on Mars. The missions we're sending there now should provide the answers.
The spacecraft with the rover will travel 470 million kilometers in more than 200 days to reach Mars. And that's the easy part of the journey. The landing maneuver is the real challenge. NASA engineers describe this critical phase as the 7 minutes of terror. The probe with the rover hits the Martian atmosphere at around 20,000 kilometers per hour and gets rapidly slowed down. For the first time ever, NASA not only released an animation of the landing, but actual video footage. It shows the lander hurtling towards the Martian surface. At 1,500 kilometers per hour, the landing parachute opens. However, because of the thin atmosphere, it can't slow the descent of the probe sufficiently. At an altitude of around 1.6 kilometers, the actual lander unit with the rover is released. The retro rockets ignite. The lander's descent slows further. At around 20 meters from the ground, the sky crane lowers the rover to the Martian surface. Touchdown! Shortly thereafter, Perseverance transmits the first pictures of the Martian surface. And for the first time ever, a rover sends to Earth an audio recording from a foreign planet. This is what the wind on Mars sounds like. Now the mission proper begins, the search for traces of life. Mars is a little more than half the size of the Earth. Where is Perseverance looking for these traces?
We are primarily looking in places where we have proof that there was liquid water, and especially where there was water for a very long time. The best examples are former Martian lakes, which we identify from the depressions they left, like impact craters, of which there are many, and into which a former river valley flowed, and, above all, where a delta has formed at the mouth of the river.
Wherever there's liquid water, we find life. At least on Earth. Water is an excellent solvent. It allows molecules to intermingle and biological compounds to form. And there used to be water on Mars.
We've since discovered that Mars wasn't always so cold and dry. For a long time it was thought that it used to be warm and wet. We now believe, or rather know, that it was cool and wet instead. So temperatures were around freezing point, sometimes below, sometimes a little above. And there was liquid water, and an atmosphere that was dense enough to keep water liquid on the surface of Mars.
Scientists speculate that a fifth of the Martian surface was covered with water for at least 1 billion years. That's an area 3 times the size of the USA. Perseverance cannot search over such a large area. Where are the best chances of finding traces of life? Tips are being provided by the Mars Reconnaissance Orbiter. The satellite is orbiting Mars at an altitude of 300 kilometers. And former lakes and rivers can clearly be made out on the images it has taken. NASA has decided to investigate an ancient river delta near the Martian equator.
A large number of deposits have been found in the vicinity of this delta that are very interesting. They include clay minerals and salts, basically everything that would lead you to conclude that if life did form, then this is the environment it happened in.
Around 4 billion years ago, there are oceans, rivers, and lakes on Mars. One day, an asteroid slams into the planet, leaving behind a crater 45 kilometers in diameter, the Jezero crater. 2 rivers fill the crater with water. A lake almost the size of Lake Constance forms. The lake doesn't dry out for millions of years. The river deltas along the former shoreline are still clearly visible today. NASA is studying the crater rocks using the sophisticated measuring instruments aboard the Mars Reconnaissance Orbiter. The crater rim consists of various types of carbonate rock. On Earth, carbonates like this are found at the bottom of lakes and oceans, where the remains of microscopic animals are deposited. This is the ideal place to search for traces of life on Mars. But what could these traces look like? Perhaps the same as on Earth. Here, complex biomolecules formed from simple chemical compounds in the oceans 3.8 billion years ago. The first single-celled organisms evolved. Microbes aggregated to form so-called microbial mats at the bottom of lakes and oceans, which fossilized over time. A new microbial film formed on the rock. Over millennia, so-called stromatolites formed. They are some of the oldest fossils on Earth. Something similar may be present on Mars too.
Assuming we do find traces of past life, it will be in the form of microfossils. That means sedimentary rocks, certain deposits, like stromatolites that were formed by cyanobacteria on Earth. This is a kind of rock today, but it was clearly formed due to the presence of these bacteria. And we hope to find similar sediments on Mars that would indicate the presence of life back then.
Perseverance receives help in its search from the air. It has a helicopter drone on board, called Ingenuity. Never before has a drone flown on an alien planet. Taking off with a helicopter on Mars is far from simple. The air here is as thin as it is at an altitude of 32 kilometers on Earth.
It will operate in a small radius of a few meters around the rover and observe things from above, something we haven't been able to do before. It will also help us decide whether it would be worth sending more instruments that can fly in future, something that's crucial for reaching places that would otherwise be inaccessible, like caves, and to look for life or maybe water and such things there.
Aside from cameras, Ingenuity has no instruments on board. The drone itself is the experiment. It's investigating how well flying in the Martian atmosphere works, and it expands the rover's range of movement.
Driving a rover like this isn't that easy. The camera might be 1.5 meters above the surface, but it only takes a small ridge, and you can't tell what's on the other side. You have to drive there to check it out, and if you can't continue, you have to drive somewhere else. It's a very tedious process. Now we can launch this small drone, and it can fly over and look behind the ridge, and we can say there's no point heading that way, we're better off turning left, and thereby extend the range and find the way to the interesting areas more easily.
It would be absolutely sensational if Perseverance were to transmit from Mars to Earth pictures of the kinds of fossils we find here in Australia. Unfortunately, it's unlikely that such fossilized microbes have survived on the surface of Mars for hundreds of millions of years. They've probably long since turned to dust due to the radiation. It's possible that all visible traces of life have been destroyed. Still, the rover may be able to find them nonetheless. With its X-ray spectrometer Pixel, it can detect the tiniest of chemical changes in the Mars rock and look for so-called biosignatures, chemical compounds that are only created by biological processes. It would be the first direct evidence of extraterrestrial life.
Life on Mars. How likely is it really? Well, 3.5 billion years ago, the conditions for it were ideal. We know that for a long period of time, the temperature on Mars was above 0 degrees Celsius. And we also know that back then, it had a vast ocean. And we have a meteorite that we know came from Mars. Many years ago, NASA analyzed this meteorite and believed they'd found microorganisms inside. So they held a huge press conference about it. It later turned out, however, that they weren't microorganisms after all, just pure geology. So to this day, we still have no evidence of life on Mars. But even if we could prove the existence of primitive life on Mars, it still doesn't mean that there might be other forms of intelligent life elsewhere in our galaxy. It would just make it more probable.
Perseverance could deliver the answer to this question. Quite literally to our doorstep, as it were, in the form of samples of Mars rock. The rover takes samples using a drill on its arm and packs them into special tubes. Then it deposits the samples at specific locations on the Martian surface.
Und dann soll ein europäischer Rover.
And then a European rover arrives, finds these little samples, collects them all, packs them into a large container, and brings them to a small launch pad where a small American rocket is waiting. They're packed into this rocket and shot into orbit around Mars. There, the rocket releases this container to orbit freely around Mars on its own. And then another European mission will come and find this container, capture it, and bring it back to Earth.
Thanks to this collaboration between the European Space Agency ESA and NASA, we'll then have Mars rock on Earth, perhaps with evidence of ancient life. It will take until at least 2031, though, if everything goes according to plan.
If we were to discover that there used to be life on Mars, not only would we know that we're not alone, but we could say with certainty that life can form in places other than on Earth. It would give us reason to continue searching, and it would be pretty sensational.
It would mean that we're no longer unique, that life can emerge not just on the Earth, but can do so anywhere with suitable conditions that allow these processes to happen. The next question is, what does this life look like? Does it look similar to early life on Earth, that is, blue-green algae, single-celled organisms, and so forth? Or is it completely different?
But if there was life on Mars in the past, is it possible that it survived until this day? On Earth, we only find life where there's water. The surface of Mars is bone dry. The low atmospheric pressure means that water would evaporate within seconds. But there could still be water beneath the surface. Scientists have discovered evidence of several lakes deep below Mars' southern polar cap. The radar aboard the ESA probe Mars Express penetrates the 1.5-kilometer thick ice. The measurements show that under it lies water. It must be extremely salty because it's liquid, despite an estimated temperature of minus 68 degrees Celsius. The high salt concentration lowers the freezing point of the water. Scientists cannot rule out the possibility that life may still exist in such subterranean Martian reservoirs today.
Many scientists actually believe that life still exists on Mars today. It cannot be on the surface, though, as the Martian surface is extremely hostile to life. So we have to drill underground. It's quite possible that there are hydrothermal vents on Mars, and that there really are life forms there still.
These are geothermal springs in Yellowstone National Park in the United States. The water here is almost boiling and is as acidic as lemon juice. Despite this, the springs are home to life, to so-called extremophiles.
The extremophiles have shown us that on Earth, too, there's life in regions we previously considered impossible, like in the ice at the poles, in black smokers, on the ocean floor, in nuclear power stations subjected to radioactivity, in salt lakes. So that means that the range of conditions in which life can exist is far greater than we previously thought.
The European Space Agency ESA is also looking for life on Mars. In 2016, the Schiaparelli lander crashed, but the mothership, the ExoMars Trace Gas Orbiter, continues to circle the planet and study the Martian atmosphere. And a European rover will soon be rolling over the Martian surface in addition to Perseverance. Rosalind Franklin can drill up to 2 meters down into the surface and will look for traces of life there.
On a positive note, we're now coordinating the program profiles of these missions with one another. So ExoMars is doing different things than the American rover. We're specifically looking 2 meters under the surface to see if there's something like life there. The American rover isn't doing that.
The NASA and ESA Mars missions are ambitious. Perhaps they will soon answer one of the most intriguing questions for mankind. Is there extraterrestrial life? And they're laying the groundwork for the next big step, a manned mission to Mars.
Wernher von
Braun, the father of the moon missions in the 1960s and 70s, had a big dream. He wanted to go to Mars. For him, the moon was just a stepping stone. In the case of the moon, you need 2 or 3 days to get there and 2 or 3 days to get back. But Mars is in a completely different league. In order to understand this, let me briefly explain the situation. At the center of our solar system is the Sun. Here it is. The Earth orbits the Sun a bit further in. Here's the Earth's orbit, and a bit further out, we have Mars's orbit. If I want to fly from the Earth to Mars, I need to follow a so-called Raman transfer orbit. This is the energetically most favorable trajectory. And there's something else to consider. If I want to meet up with Mars here, when I set off from Earth, Mars must be roughly here. Because at the same time as I'm flying across here, Mars is moving toward this point as well. So I meet up with Mars here. But here's the thing, I obviously want to return to the Earth again. And to fly back, I need to follow another Raman transfer orbit. But when I set off, the Earth can't be just anywhere. It has to be roughly here. This means I need 200 days to get there. No more, no less. It's pretty much exactly 200 days. 200 days to get back again. And have to spend a little more than a year on Mars. So altogether I need 2.5 years for a complete Mars mission. And I can only do this every 2 years, because the Earth and Mars are only in this constellation every 2 years. We have the rockets necessary for such a mission, both NASA and Elon Musk. But that's not the problem. The real problem is guaranteeing the technical reliability of the mission for the entire 2.5-year duration. And in order to do this, we need the moon. We can use it as a proving ground to show that we can do it.
But before we set off to Mars, we're returning to the moon. Following the Apollo program of the 1960s and 70s, NASA has launched a new, ambitious lunar program, the Artemis program, named after the twin sister of the Greek god Apollo. In 2024, over 50 years after the last flight to the moon, Apollo 17, a human will once again set foot on the lunar surface. And this time, we're coming to stay. From 2028, there will be a permanent research station there.
Fortunately, the attention of many countries, states, and space activities is once again on the moon. It wasn't always this way. It had been forgotten. For a while, the moon was considered to be just a dead rock. But we now know there's water on the moon. We know that there's helium-3 in the moon. The moon is much more exciting than we think, which is why there's now a worldwide movement to fly to the moon as well.
The moon has become scientifically interesting again, and it's of strategic importance. The destination of the Artemis missions is the southern polar region, because there's water ice there. The moon is not as arid as it was long presumed. SOFIA, the flying telescope of NASA and the German Aerospace Center, detected finely dispersed water molecules in the moon dust. Not much, only about 1/3 of a liter per cubic meter of lunar regolith. Perhaps it was brought to the moon via small meteorite impacts encapsulated in tiny glass pearls. Water is the key raw material on the moon, too. Astronauts need it to survive. And water can be split into hydrogen and oxygen, which make rocket fuel. Construction of a new space station that will orbit the moon is scheduled to start as early as 2023. The Lunar Orbital Platform Gateway will be the counterpart of the International Space Station. Like the ISS, it will consist of separate modules and is a collaboration of various countries and private aerospace companies. In the future, astronauts will travel to the moon via the Lunar Gateway.
The Lunar Gateway is a kind of bus stop orbiting close to the moon from where it's easy to descend to the lunar surface, and that can be used as a staging post. It's a big program, and NASA naturally imagines it as being the stepping stone to Mars.
The moon will be our proving ground, our research laboratory, perhaps even our gas station and springboard to Mars. NASA presents the new spacesuit. A woman is to set foot on the moon for the first time as part of the Artemis program. The new suits offer substantially more freedom of movement than previous models. They work at temperatures ranging from -150 to +120 degrees Celsius. They're intended to be used on later Mars missions too. Life support systems for the astronauts, habitats to protect them against the deadly radiation and cold, the mining of water and oxygen, and the production of rocket fuel. All this is to be tested and perfected on the moon.
I would say our moon is a bit like an extra continent. It's really close, practically on our doorstep. We saw that with Apollo. You can fly there in 3 days and back in another 3. And 100 years ago, you couldn't even get from England to America in 3 days. So I'm pretty sure that the moon will remain a target.
It would make flying to Mars much easier if you could use it as a stopover, as it were. You'd just have to first head to the moon, and then you can board the spacecraft that will ultimately take you to Mars. You wouldn't have to escape the Earth's atmosphere with this vehicle, and thus you could have a break during the long flight in a sense.
Mankind is getting ready to take the next big step. And as in the 1960s, the journey begins with fire and smoke.
The key to a successful flight to the moon, and indeed Mars, is a highly efficient and reliable rocket. Because for every ton we have to transport to the moon, we need 100 tons of fuel. Every % of efficiency really matters here. So, what rockets do we have? Well, in the middle here, we see the old Saturn V from the 1960s. These are the 2 new rockets that are currently under development. On one side, Starship from SpaceX, so Elon Musk. And on the other side, the SLS, which stands for Space Launch System, from NASA. Incidentally, the rockets are about 120 meters tall, which is roughly the height of the Cologne Cathedral. And each rocket weighs about 3,000 tons. It's interesting to note that although the objectives of the new rockets are the same, their development processes were completely different.
The Space Launch System, the biggest, most powerful, and most expensive launch vehicle in the history of NASA. Depending on development stage, it will be able to deliver a payload of up to 130 tons into low Earth orbit or 45 tons to the moon. The SLS is being built by Boeing using proven technology. The solid rocket boosters and upper stage engines stem from the Space Shuttle program, which was developed in the 1970s.
It's definitely state-of-the-art, technology-wise. The Space Shuttle main engine is basically the most efficient engine ever invented and built in the history of mankind. The only problem is that it's very expensive.
Because there aren't enough shuttle engines left for the Artemis program, NASA has ordered 24 new ones at a cost of nearly $150 million apiece. The SLS is not reusable, so 4 of these engines are lost with each launch. The cost of an SLS rocket launch is estimated at around $2 billion US, and developing the SLS devoured $20 billion even before the first launch.
It's a question of risk. If I, as an institutional service provider, want to do something, I want to minimize the risk involved. I'm using public funds, and I want everything to function 100%. If I were approaching things as a private entity, I would allow more risk. As a result, I have a chance of achieving the same goal with lower costs.
Making space travel radically less expensive is the goal of SpaceX founder Elon Musk, and also Stefan Brischenk, COO and Chief Developer of Rocket Factory Augsburg. The Bavarian rockets aren't intended to fly to Mars, but rather to cost-effectively put small satellites into low Earth orbit. The principle, industrial rocket production instead of rocket science.
We're trying to approach things from an industrial perspective. We come from an industrial background. You can picture it like this. We're more like a car workshop that has the goal of building a cost-effective rocket. We're not starting in a lab or clean room and trying to push the boundaries and achieve the maximum that's technically feasible.
That's why it looks like it does here. High-tech meets craftsmanship. Rocket Factory fabricates complicated components itself. Others, like the large stainless steel tank, come from subcontractors, and partly from the automotive industry. The engines are 3D printed.
It speeds up the development process, as we can modify things and try them out quickly. For instance, if we notice that the heat buildup at a particular point is too great, we can change the design of the cooling circuit to increase cooling there. That is, I can program it, print it out, finish it, and test it immediately. It's essential that we can precisely replicate parts later on. I only need to configure this machine once to get the same result every time. This will become important when we increase production from 1 rocket to 20. It allows us to scale things up easily. We just have to buy more 3D printers, set them up properly once, and then we can print engines like on an assembly line.
Mass production is the basic concept of SpaceX and Elon Musk, too. The new giant rocket ship, Starship, is intended to take payloads of up to 150 tons or 100 astronauts into space. It is intended to replace all other SpaceX rockets, put satellites into orbit, and fly to the International Space Station, the Moon, and ultimately to Mars. The Starship consists of 2 stages. The first stage, named Super Heavy, is designed to take the rocket fitted with 31 Raptor engines into Earth orbit. Here, the upper stage separates from the first stage, refuels if necessary, and sets off on its mission. In August 2020, the first Starship prototype flew to a height of 150 meters before landing again. Following the principle of trial and error, SpaceX rapidly develops its technology further. Risks and setbacks are factored in, and they're real. In December 2020, the 8th prototype climbs to an altitude of over 12 kilometers. The rocket quickly gains height, then starts its descent, flips horizontally to slow down as planned, and then vertically again, ready for touchdown. The landing itself, however, doesn't go quite as planned. Barely 2 months later, the next flight with rocket number 9 meets a similar end. "We've just got to work on that landing a bit," was the laconic comment from SpaceX.
At SpaceX, they call it sparse matrix engineering. It means that engineers make decisions without filling in all the blanks before proceeding. I wouldn't consider it shooting from the hip, but you make decisions faster in order to move forward more aggressively. And there are naturally risks involved. The engineers working there are allowed to take greater risks and achieve their goal faster as a result.
SpaceX estimates that a Starship launch will cost $2 million. That would be 1,000th that of an SLS launch. The reason? Industrial mass production. Elon Musk wants to build up to 1,000 starships in 10 years, and the Starship is completely reusable. And that's not the only thing that speaks in favor of the Starship concept compared to the SLS. Its Raptor engines run on oxygen and methane. Both can be mined on Mars for the astronauts' return journey to Earth. But for humans to survive on Mars, it will take a lot more than that.
So, what are the living conditions like for humans on Mars? Let's take a look at the atmosphere first. The air pressure is just 1/100th of that on Earth. This means you have to wear a pressure suit at all times. And if you always walk around with one of these on, temperatures of -60 to +20 degrees Celsius at the equator are no problem. But what's the deal with the infamous Martian storms? Well, with such a thin atmosphere, they're more of a gentle breeze. One issue is the CO2 atmosphere. There's no oxygen up there, so you'd have to wear oxygen cylinders on your back all the time. There are basically only two real problems. One is the cosmic radiation that bombards the surface unimpeded. Let's put it like this. A person on Earth has a 20% risk of getting cancer. Spending 2.5 years on Mars will increase this by another 20%. So 40% in total, which is quite high. But the really big problem is that the vast amount of fuel needed for the return journey to Earth would have to be manufactured entirely on Mars.
Future astronauts on Mars will need protection from the vacuum, cold, and radiation. They'll need air to breathe, more specifically, oxygen. This is present on Mars, in abundance, in fact.
Oxygen. There's a lot on Mars. Mars is also known as the red planet, and it's red because it's rusty. This is iron oxide, which means there's a great deal of oxygen in the Martian crust and rocks. There's also a lot of oxygen in the atmosphere, too, albeit not as pure oxygen, but bound as carbon dioxide. Whether we split the carbon dioxide or extract the oxygen from the rocks because we want to mine iron anyway, the element oxygen is definitely present. The only question is, how easily can we extract it, and how efficient and reliable is the process?
The Perseverance rover is tasked with testing it, and that's why MOXIE is on board. The device will use electricity to split CO2 in the Martian atmosphere into oxygen and carbon monoxide. MOXIE is about the size of a car battery. Future systems would have to be 100 times bigger in order to generate enough oxygen for the astronauts to breathe. The Mars travelers will also need oxygen for their return flight as part of the rocket fuel. The other part, hydrogen or methane. Both could likewise be manufactured on Mars.
When we eventually fly to Mars, it's likely that 3 or 4 spacecraft will have been sent in advance with material, equipment and fuel, and also a small plant to synthesize fuel to get them home again. It's a very different proposition to a moon mission, where you fly there, stay for a few hours and then fly back again. Things won't be quite that straightforward with Mars.
The astronauts will have to live on Mars for over a year before the next window for a return flight. Perhaps in modules like this. It was developed by Christiane Heinecke of the Center for Applied Space Technology and Microgravity, ZARM, at the University of Bremen. A module from the Moon and Mars Base Analog Project, or MAMBA for short, stands in a laboratory hall at the center. ZARM scientists have already spent 2 test weeks working in here, albeit without the life support systems that would be necessary on Mars.
If I were to simply go outside on Mars, I'd either suffocate or experience a very unpleasant death anyway. This habitat must ensure that I can breathe. It has to withstand the pressure difference and protect me from the cosmic radiation. Though Mars has a thin atmosphere that filters out a small amount, a great deal still comes through.
6 modules like this will later be joined together on the Moon and Mars to create a self-contained system, a so-called habitat, a living space for the astronauts. The individual modules serve different functions and are equipped differently, as a laboratory, a workshop, or for sleeping.
Our plan is to construct a large artificial cave around the habitat with moon rock or Mars rock. Whether it will be made by 3D printing, using individually sintered blocks, or simply by piling up rocks is irrelevant. In the end, there'll be a thick layer of rock surrounding the habitat to protect it from the cosmic radiation.
There are basically 2 concepts for such habitats: rigid metal constructions like the Mamba modules, or inflatable modules made from some sort of fabric or foil. With this concept, developed by ESA, the modules are buried in moon craters to protect them from the radiation.
The big advantage is that the transport volume is relatively small while offering a large amount of space when erected on site. The disadvantage is that you then have to assemble everything on site. You have to bring in all the tools and equipment, through the moon dust, airlocks, in and out. What you save on transport, you trade for all manner of problems down the road. Which is why we said for the first base on the moon or later on Mars, it will be much easier if we have the habitat more or less completely assembled as a single module. The finished module will naturally be much heavier and larger than an inflatable one, but once it's on the moon, it's finished.
Scientist Cyprien Verseux is conducting research at ZARM on cyanobacteria. Also known as blue-green algae, they could play a key role when it comes to living on Mars. They grow by photosynthesis, can generate oxygen and extract nutrients from rock. With their help, oxygen, fuel, and even food could be produced on Mars. To do this, the cyanobacteria basically require gases found in the Martian atmosphere and water.
You could feed them almost directly with what you find on Mars. And once you've grown them, you can use them for making oxygen, for making dietary protein, but you could also use them for making nutrients for other organisms, like plants or other microbes. And like this, make a small-scale ecosystem, which is based almost directly on what you find on Mars, and that can produce most of what astronauts need to survive.
How well do cyanobacteria grow under Mars-like conditions? This is what Verseux is investigating with his experimental setup he designed himself. The bacteria are grown in these flasks. The pressure, composition of the air, and temperature are different in each one, and they differ only slightly from the conditions on Mars.
You want to be as close as possible to the Martian atmosphere so that the system would be easier for engineers to design. Because if you have a big pressure difference between inside and outside, you need something very sturdy and so very heavy. So we're trying to find out how close you can get to Martian conditions while still having bacteria that can grow efficiently.
Future Mars explorers won't have to subsist on algae alone, of course. They will likely bring a large portion of their food from Earth in the form of freeze-dried rations, like the astronauts on the ISS.
I think it will be a combination of different approaches. You'll have freeze-dried food, but you'll still end up having to cultivate fresh plants, not least because you're in this rocky desert. You want to see a plant now and again.
Growing vegetables in a greenhouse works, even if the conditions outside are not exactly hospitable. This has been demonstrated by the Eden ISS greenhouse in the Antarctic. A year-long test of vegetable cultivation for Moon and Mars missions was conducted here on behalf of the German Aerospace Center. The harvest, 300 kilograms of salad plants and vegetables, as well as herbs and even strawberries. And all this from just 13 square meters of cultivated space, without soil or sunlight. Instead, electronically controlled and optimized. Although the team at the German Antarctic station Neumeier 3 was cut off from the outside world, the scientists were served fresh vegetables on a regular basis.
Das stimmt.
That's right. We could grow vegetables in greenhouses on Mars. Incidentally, the movie The Martian depicted this in an authentic and, above all, very vivid manner. So that's how humans could colonize Mars. You could ask yourself, why should we bother? And the answer is, because then we actually could. And the next question is, when will all this happen? Well, it certainly won't be before the end of the 2040s. Probably more like the 50s or maybe even the 60s before we're ready.
SpaceX founder and chief engineer Elon Musk wants to save mankind. If the Earth should one day become uninhabitable due to an asteroid impact, the eruption of a supervolcano, or for some other reason, we'll need a foothold on another planet.
The main reason I'm personally accumulating assets is in order to fund this. So I really don't have any other motivation for personally accumulating assets except to be able to make the biggest contribution I can to making life multiplanetary.
Namely, on Mars. If it were up to Elon Musk, there would be self-sufficient cities on the red planet by 2050. He estimates that it will require 1,000 starships to bring the material and crew to mankind's new home. It will take 20 years to transport and build the infrastructure, from the fuel plant to the pizzeria.
The goal is get enough tonnage to Mars and enough people to make Mars self-sustaining as quickly as possible. 100,000 tons, maybe 1 million tons. So you can't be faffing around with these expandable rockets. They're a joke. They're absurd. Even Saturn V is tiny potatoes.
Another reason why SpaceX's Starship is not only huge, but designed to be completely reusable too. Thanks to industrial mass production, the rockets are designed to bring down the cost of a flight to Mars from around $10 billion per seat to $140,000. But is this actually realistic?
The vision of traveling to Mars has always fascinated people. It takes people who can drive things forward and have or can mobilize the necessary resources. Otherwise, you can't turn a vision like this into reality. It will happen sooner or later.
Elon Musk is doubtless a visionary, and he's accomplished a lot, an incredible amount, which is why I admire him. He's a great businessman, too. He's negotiated great business models with NASA. He's consistently taken a visionary approach and done things we simply couldn't have.
Ich halte Elon Musk für einen sehr großen Showman.
I consider Elon Musk to be a great showman who made his money in completely different areas and was probably fascinated by space travel as a child and said, I want to do that when I grow up too. But if you look at his projects, you have to ask what have they actually accomplished thus far. He's got as far as the International Space Station, 300 kilometers above the Earth. But when you consider all the things he's talked about, when we'll be on Mars and so on, well, I'll see how things go over the next few years.
Ich gucke mir das an die nächsten Jahre.
Even if humans do actually settle on Mars in 50 or 100 years' time, Mars is no second Earth. But perhaps it doesn't have to remain an inhospitable desert. Terraforming could, in theory, turn the clock back 3.5 billion years and transform the red planet into a blue planet once again.
First, you need to start heating it. There are different ways of doing it. I mean, some people are suggesting having some mirrors in orbit to, focus sunlight. There is an extreme solution that Elon Musk famously talked about, which would be to drop some nuclear bombs on the poles. There are many, many ways it could be done, or it could be also starting, bringing some greenhouse gases. And then once you start heating it a bit, then the carbon dioxide ice would sublimate. So it basically you would have carbon ice that would become carbon dioxide as we know here. And then with the greenhouse gas, it would heat more, which means that more carbon dioxide would come out and so on. And then once it's warmer, you could start thinking of bringing, cyanobacteria, for instance, that would do photosynthesis, create oxygen and so on. So that would be a very slow process and you would have several steps, but there are several ways in which it could be done.
In time, you could eventually cultivate an increasing number of ever more discerning plants, until at some point the atmosphere is dense enough for future Mars inhabitants to venture outside without pressure suits. It would take 500 to 1,000 years. It would take even longer before sufficient oxygen has accumulated in the atmosphere for it to be breathable, probably around 1 million years. Unfortunately, the hard-won Martian atmosphere wouldn't be permanent, as Mars lacks a protective magnetic field. The radiation would blow it away again after a few 100 million years, the way it did 3.5 billion years ago.
Terraforming Mars means making it blue and green. In theory, say the scientists, it ought to work just fine. Whether it actually works in practice remains to be seen. So what does the future of manned spaceflight look like? It's easy to answer. First, we'll fly to the moon, have a manned moon base, then to Mars in the 40s or 50s, including a permanent base. Will we then venture even deeper into the solar system? Not a chance. Why? Well, the temperatures present somewhat of an obstacle. If we fly toward the Sun, to Venus or Mercury, the temperatures are in excess of 400 degrees Celsius. If we fly away from the Sun to the gas giants like Jupiter and beyond, the temperatures fall below minus 200 degrees Celsius. These are not conditions for human beings. Even the moons are too cold. The only things out there that could be of interest to us are the oceans beneath 2 of the moons. But we can visit them with unmanned missions. Whatever happens, our moon will always be there for us to use as a proving ground. And I have to say, I'm very grateful we have it.
Mankind is about to take a giant leap, like Neil Armstrong in 1969. Astronauts are set to return to the moon and operate a research station there. Experts are divided as to whether or not humans really will fly to Mars in the near future.
From a technical and engineering perspective, it would be feasible to fly to Mars within the next 15 to 20 years. What's always been lacking, however, is the political will to actually do it, and therefore the funding to really see it through now.
I don't think we'll see astronauts heading to Mars in the near future. Mars isn't like the moon that constantly circles around us. Mars has its own orbit around the sun. This is why we only meet up with it every 2 years. And it's also why a trip to Mars and back takes 2 years. And when you consider the radiation, technology, and all the other issues, it's simply too difficult and complicated to be attempted at the moment.
The big question is whether we will have the investment and the focus needed to do it. I'm quite hopeful that it will happen, otherwise I would not be working on that. I would be losing my time.
Eine Reise zum Mars.
A trip to Mars is such a huge undertaking that the entire world would have to cooperate. It won't be one American. It won't be a Musk. It won't just be NASA. Rather, the American, Chinese, Russian, and European space agencies will have to work together. In that sense, it's good news, because if everyone is working together, it means we've solved all the other problems in the world for the time being.
If enough money can be made from space travel by mining raw materials on asteroids, for instance, the question of funding won't come up anymore. The boundaries will then be pushed even further.
We could go to Ceres or any of the asteroids, the moons of Jupiter, although there'd be quite high radiation around there, and then out to Saturn, eventually getting out to the sort of Kuiper belt or cloud and that kind of thing, the outer solar system. So Starship, once you have propellant depots, you can kind of like planet hop or moon hop around the solar system.
This is no doubt a very far-off vision, but in the end, every great journey begins with one small step.
To sum it up, we will return to the moon before this decade is out. There, we'll test the technologies that will be needed to send a manned mission to Mars. This will likely happen in the 2030s. But it probably won't be until the 40s that we'll have a permanent research station there, because that won't exactly be cheap. Whether in the 2040s or even the 50s is pretty much secondary in light of the fact that these first Mars flights will no doubt go down in history as one of the greatest achievements of humankind.